Am I audible? Sonali ma'am, am I audible?
Yes, madam.
Vishal Singh sir have joined, I think. Sir, are you there? Okay, dear participants, the session will begin shortly. Kindly ensure the following before we proceed. Please mute your microphones to avoid any disturbances. And questions will be addressed in the last 5 minutes of the session. So kindly note them down as the session progresses. And this session is being recorded for future reference. We'll wait for some time for the sir.
Vinaya ma'am, Vishal sir is in meeting and I have made him presenter as well. So he
Okay.
can start his microphone and he can proceed. Sir, are you there in meeting? Dr. Vishal Singh, sir, are you there in meeting?
Shall I start, Anjali ma'am?
No, let them speak. Let them, are they ready or not? Let me confirm that, na?
Okay.
Or will you please call her, call him again?
I just call him.
Ha.
Anjali madam.
Yes, ma'am. Yes, ma'am.
Please unmute Vishal sir.
He can able to unmute. He can able to present as well. I have done him presenter and I have done spotlight on also him. So he can able to present now and share.
Sir,
Right
sir,
now,
can you try to unmute from your side?
Vishal sir, you can unmute your microphone. I have given you authority. Is there
I'll check.
another voice,
I'll
sir?
just check. Anjali ma'am, I'll just message you on WhatsApp. What is happening?
Okay.
Ma'am, shall I proceed with the introduction part? If sir has already joined.
आपके पास हेडफोन या ये है? हाँ हेडफोन। हेडफोन से आपका हेडफोन का माइक और ये ओके हो जाएगा, वर्क हो जाएगा। हेडफोन इसमें लगा के अच्छा ठीक है, लेट मी चेक मैडम।
Good afternoon, Vishal sir, you are audible.
I'm audible now? You are
Yes, sir, you
audible.
are audible.
Okay, fine, thank you. You can't able to present now because Vinaya ma'am is presenting your slide, introduction slide. After you can, sir. Okay. Okay, all right, fine, thank you.
Okay. Welcome, sir. Good evening, everyone. A warm welcome to all of you to the Faculty Development Program organized by Bharati Vidyapit's College of Engineering for Women in association with NIH Roorkee. We are excited to have you here for this enriching experience. It is my privilege to introduce our esteemed speaker for today, Dr. Vishal Singh, a distinguished scientist in the field of hydrology and climate studies. Dr. Singh is currently serving as a Scientist D at the Center for Cryosphere and Climate Change Studies, National Institute of Hydrology, Roorkee, under the Ministry of Jal Shakti Government of India. With over 14 years of research experience, Dr. Singh has made significant contributions in water resource engineering, snow glacier melt runoff modeling in the Himalayas, rainfall runoff modeling, glacier dynamics, climate change downscaling, flood modeling, and the application of machine learning in hydrological studies. His experience in remote sensing and GIS techniques has been instrumental in advancing research in these critical areas. Dr. Singh holds a PhD in civil engineering from IIT Guwahati and has further enhanced his research experience through postdoctoral studies at North Dakota State University, USA, and Nanyang Technological University, Singapore. He has an impressive academic record with over 45 peer-reviewed international research publications and is an active member of prestigious scientific organizations such as ISRS, IIH, and AGU. Beyond his academic and research contributions, Dr. Singh is actively engaged in several national and international R&D projects, playing a pivotal role in shaping policies and strategies related to climate change and water resource management. We are privileged to have him with us today, and I'm sure his insights will be invaluable to all of us. Over to you, Dr. Vishal, sir.
Thank you, madam, for your nice introduction. And I hope that in my today's lectures, most of the participants will be beneficial for their purpose and other things. And at last, we can discuss. And I also would like to tell that if you have any doubt, any concern while presenting my lecture, so you can ask your queries or we can discuss in detail in the last. Okay. So
Yes, sir.
I'm
We
just
have
going.
the session at the end of the session. Okay,
Okay,
over to you, sir.
thank you. So I'm going to share and please inform me once it is visible to you. So I have shared my presentation and please let me know if you are able to see that.
Yes, sir. Your slides are visible.
Okay, thank you very much. So now I can start. So my topic for the today's lecture is mitigation and adaptation strategies for climate change scenarios. So I can tell that I think in previous lectures you have been briefed about the impact of climate change on different applications in the especially in the field of water resources development and management. And here in this lecture, I would like to discuss some more adaptation policies, mitigation strategies, and how we can minimize the impact of climate change in different fields, we can say. So here, first, I would like to discuss more on the IPCC reports that is recently published
and it tells more on the climate change and their observations, or we can say the consequences of the climate change that we are getting in the world. Many of you are already aware about this report, and who they are not aware about this report, they must go through it, and they can read the report, and it tells a lot of things about the happenings of the climate change across the world as well as in Indian scenarios. What is all this report? I mean, what talks about this report? So I just want to give some brief about that. So, in the history of IPCC, as you know, that IPCC is the nodal agency which generates the different climate scenarios, considering different aspects of the warming world. We can say that in the third assessment report, when it came in 2007. So we talked on the increasing concentration of the greenhouse gases, and what will be the consequences of the increasing of these greenhouse gases in terms of temperature increase, and a lot of things we have seen that. Then in 2011, another report came, and now the latest report came in 2021, then 2022. And it talks about the socio-economic aspects also, along with the different consequences of the warming world, like greenhouse gases concentration, aerosols concentrations, land use changes, and so on. Number of working groups were formed, and each working groups, the different aspects have been produced as per the observations. Basically, it deals with the different kind of scenarios that is based on the different historical observations. Number of data sets were generated, and the number of models were generated, and then number of projections were made in the history, to analyze the historical scenarios as well as how the climate change will impact in the near term as well as in the far terms. So physical science basis, some observations were made. Then the second version of the report came in the 2022 that discuss about the impacts, adaptation, and vulnerability. Then another third version of the report came in 2002. Then that deals with the mitigation of the climate change impacts. So here I would like to highlight you some of the major observations that we have noted down based on this IPCC assessment report 6. So how far away is 1.5 degrees centigrade of warming? So in case of assessment report 5, we have talked more on the temperature warming. I mean, different RCP based scenarios were produced, and number of experimental scenarios were generated, like mitigation scenarios, then moderate emission scenarios, then high emission scenarios. So currently, in that time, we were more talked on the 1.5 degree centigrade warming. But now, if you see the current scenario, so we have already crossed this limit. That is discussed more on the IPCC assessment report 5. And after coming this IPCC assessment report 6, now we can see that now we are at the end of this 2024. We have crossed the limit of the increasing temperature, like 2 degrees centigrade. And in some areas, you can see that the warming is accelerated, and that is crossed even more than 2 degrees centigrade. So here, I mean, if you see this figure, I can highlight here, like, let me open this pointer. So if you can see how the temperature is warming, and if you see the polar regions across the world, that is more affected due to warming, or we can say the increasing rate of the temperature. So definitely there will be some negative consequences that we will discuss in the coming slides, and what could be the mitigation policies or strategies that we can develop to mitigate the impact of the climate change, that we will discuss. So now I'm going to talk on the how the observations were made as per the historical records under the IPCC assessment report 6. So here you can see that warming of 1.5 degrees centigrade will accelerate the weather extreme across the world. So I mean we have already crossed this limit and somewhere we are falling in this range like 2 degrees centigrade. If you see if somebody has already worked on it, so if you have analyzed the past historical temperature records like time series data sets, from like the temperature data, if you have analyzed in terms of mean temperature, in terms of minimum temperature or maximum temperature, so you can see that in most of the regions we have found that there is a significant increase is recorded in terms of temperature. So what could be the consequences of the temperature increase? So here, being a hydrologist, I will more discuss on the hydrological aspect. So if you in the first concern, we can see that the high and low extremes events are increasing in the different regions across the world, and in India also we are getting the same observations. Like in terms of increasing in terms of high extreme events, we are seeing the more consequences of the climate change in terms of floods. And while in the summers, we are seeing the more consequences in terms of droughts. So these are some consequences that we have observed in the historical records, and this is happening because of the warming of the world. So how much warmer will the world get in the future? So like if you talk about the AR6, so you can see that the Earth will be 1.4 to 4.4 degrees centigrade hotter than the pre-industrial levels by the end of the century, depending on the weather emissions are rapidly cut to net zero on the continue to rise. So here I have shown you one figure, and this figure tells how the temperature increases in the future as compared to the historical times. So the IPCC assessment report 6 basically based on the CMIP 6 climate models based projections. And in the assessment report 6, in the latest CMIP 6 projections, if we talk about, so they have added the socio-economic aspects. So earlier we used to use the RCPs and now we are using the SSPs. So in SSP 1, SSP 2.6, SSP 4.5. So these are the different experimental scenarios that actually tells about the radiative forcing level in the atmosphere. I mean, that defines how the temperature is affecting the warming. So if you consider this the upper limit, so that is showing the SSP 5 like 8.5 uh, radiative forcing level, and the unit is watt per meter. So similarly, if you see that there is a sharp increase in the temperature trends, you will get here based on the IPCC assessment report 6 observations. So these CMIP 6 model scenarios generated from 2015 to 2100, like 2100. So you can see that different experimental ranges are there. So this is the down line boundary condition, and this is the upper boundary line condition. So if you consider the different experimental scenarios, so you can assume the different rate of temperature increase. Like if you consider this 1.9 emission scenario, so you can expect 1.4 degree centigrade increase of temperature. And if you consider this 8.5, so you will assume like the temperature will be rise in the future like 4.4 degrees centigrade. So these are the different emission scenarios, and these are the experimental observations developed as per the historical trend analysis. So how these temperature warmings are affecting in terms of the rainfall. So rainfall is the main hydrological variables that we deal in the different hydrological process. And so how it is affecting by the climate change, that I have noticed some observations from the climate change. So assessment report 6, as per the assessment report 6, if you see that, so I think the frequency and intensity, if we talk about, so most most of the regions are showing that the frequency is also changing and the intensity of also changing. So we can see that earlier we used to get the moderate amount of the rainfall like in the whole day, but now the duration is limited and the duration is reduced, but the intensity is increased. So in a shorter time, we are getting the more intense rainfall, and this is happening because of the negative consequences of climate change, as reported by the AR6. So number of observations were made. I'm not going to read this, but if you are interested, you can go and you can read the IPCC assessment report. So in terms of snow and ice, so most of the areas, if you see, especially in the polar regions, so here in this figure, I have highlighted the different areas where you will find the significant change in terms of snow and ice. So in the Arctic and Antarctic, both regions are affecting because of the temperature increments. And here, especially like in Indian concerns, we are more interested about the Himalayan topography and hydroclimatology. So that is also mostly affecting because of the temperature warming, and we are seeing that the decrease in the glacier mass, like we are seeing that the glaciers mass is reducing, and as well as the snow mass is also changing, and high variability we are getting in terms of snowfall in the high Himalayan areas, and because of that, the runoff fluxes are changing, especially in the downstream sections. So these are the negative consequences that we are getting while we are talking about the climate change impacts. So now I have listed also the Asia specific observations that we have noticed as per the assessment report. So if you can see that as per the recent historical observations, heat extremes have increased while cold extremes have decreased. And these trends will continue over the coming decades. So that means in the coming future, these extremity will be more intense as we are moving from one experimental level to the another higher experimental level. And like we are talking about the Himalayan areas, so you can see that like the glacier belt runoff is increasing because of the increasing glacial retreats. And because of that, we are getting the more runoff, especially in the summer season, because of the accelerated snow and glacier melting. And in the monsoon season and in the summer season, late summer season, we are getting the less runoff. So this shifting kind of thing also we have noticed. And because of the increasing runoff, so definitely the sea level will increase. And if you can imagine like if the temperature will increase like 4 degrees centigrade or greater than this range, so definitely at the end of this century, around 70 to 80% glacier mass we will lose, and because of that, the runoff will be higher, and especially in the downstream sections, and the sea level will rise. And you can see that a number of coastal cities that will be submerged, due to increasing sea level rise. So these things can be happen, but this time, if you talk about the present time, so we are crossing like 2 degrees centigrade temperature increase limit. So we are expecting more if we don't cut down the carbon emission. So some India specific observation, if we talk about, so in India, we have we have seen number of regions where the temperature increments are observed. Like if you talk about the Himalayan areas, so around 1.5 to 2 degrees centigrade temperature increases we have recorded. Then global warming will have serious impact on the mountainous ranges, like we are talking about across the world also, and Himalayan areas will also be affected. So, and because of this increasing temperature and all that, the monsoon phenomena will also be disturbed. Like here we are talking about the temperature increase. So if you know that in the western Himalayan regions, mostly governed by the winter season rainfalls or precipitations. So in the higher Himalayan areas, mostly we are dependent on the western disturbances, and because of that, the snowfall occurs due to the western disturbances. And if this climate change will will be continued and the temperature rises will be continued, so this western disturbances phenomena will be disturbed, and in the summer season we will get more intense rainfall, and in winter we are getting low amount of the precipitation, especially in the higher Himalayan regions, and the snowfall and the precipitation ratio will be decreased, like precipitation versus snow and precipitation versus rainfall will increase. So, therefore, we can assume a more rainfall in the Himalayan areas as compared to the precipitation, especially in the winter season. And this will reduce the overall mass in terms of snow and glaciers. So here I have shown you some plots which compares the temperature changes, especially in the Indian regions. And here we have taken the observations from the earlier versions of the climate model scenarios like CMIP 5. And under this, we have plotted the temperature changes in terms of major maximum temperature, in terms of minimum temperature, and how the temperature is going to increase in the Indian areas. So here if you see that and this analysis is divided into two basically parts. One is the near term changes and far term changes. So here I am showing you the near far changes. So here if you see that this is the average phenomena of the maximum temperature and this is the minimum temperature, the average annual minimum temperature and average annual maximum temperature. And if you see in the near term scenarios like 2006 to 2050, so if you see the northern areas of India, that is getting more heat than the southern areas. So if you see this reason, so this is more intense in terms of getting warmer. So here you can see the total changes in the absolute temperature ranges in terms of degree centigrade. So if you can see that in Indian region, as per the CMIP 6 data, we have analyzed here, and you can see that it is changing from 0.5 degrees centigrade to 1.9 degrees centigrade. So clearly you can see that in terms of maximum temperature, we are getting more. And when you will see the similar trend in terms of minimum temperature, so this is more intense here. If you can see that, especially in the northern regions. And in the northern regions, you can see that more warmer will occur as per the IPCC projections. So these are the temperature increments we can assume in the coming decades or coming times, especially in India. So similarly, if you see the long-term changes, so as I am saying that because of different negative consequences of the climate change, if you see, so the temperature increases will be more intense as IPCC is already predicted, and here you can see that. So it is increasing like 1.5 degrees centigrade to 2.9 degrees centigrade, like 3 degrees centigrade. So in some areas, we have already crossed this 1.5 degree centigrade limit, and we have reached up to 2.9 degrees centigrade. So this kind of temperature increases we can observe, and in terms of in the far times, like long-term times, like 2006 to 2050 and 2056 to 2100. So this is the difference time period that we have compared here. And based on this time, two different times, if you compare, so the maximum increase of the temperature is expected to be changed around 3.1 degrees centigrade. So this kind of warming we can assume in the coming years in India. And these are the observations that we have noticed, like in terms of precipitation changes. So here historical versus near far changes I have shown you. So in this, if you see this scale, So this is historical scenario. This is like 2006 to 2050. And this figure is showing the percentage of change between these two times, like time series 1 and time series 2. So time series 1 represents the scenario year from like 1961 to 2005. And this scenario represents the future time, like near future scenario time, like 2006 to 2050. And if you compare the precipitation or rainfall changes in India, so here you can see that the percentage change limit. So the scale is showing you like the temperature change like -100 to +100. So -100 representing the areas. The blue color is actually representing where the precipitation or rainfall will be decreased. And the red color areas will be highlighting where the rainfall will assume to be increased in the future. So here we have taken the different climate models, and each model actually representing almost the same phenomena or pattern. So in this area, if you see that, especially in the Himalayan belt, or we can say the northern part and the eastern part of India. So in this region, basically we are getting less rainfall as compared to the historical time in the near future time. And in this area, we are getting like the more higher intense rainfall. And you can also see that in the last few years, we have observed a number of extreme events in terms of high precipitation events during summer time, especially in the western Himalayan regions like in Jaipur, Jodhpur, and some cities like in Gujarat. Okay, so these are the trends that we have actually observed in the different models. So similarly, if you see that in the most of the areas, we are getting the higher rainfalls if you consider the long-term changes as compared to the historical changes. So here in among all the models, climate models, you can see that most of the areas showing the increase in the rainfall. In some areas, we are showing the decrease, like here in the northern areas. So this is the variability that existed in the climate model, and these models are mostly showing in some areas we are getting the higher rainfalls, in some areas we are getting the less rainfalls. And these are some trends that I can show you, like in terms of precipitation extremes. So here actually we have calculated different rainfall extreme indices. So this extreme indices will tell about you how the rainfall is changing in terms of frequency, in terms of intensity. Like frequency based indices we have calculated, and we have calculated the intensity based indices. So here four indices we have calculated. So one is the wet days, another is the dry days. So and this is the rainfall events which falls between the 10 mm to 30 mm events on a particular day, and these are the events that falls between the 2 mm to 10 mm rainfall in a particular day. So how these rainfall events are changing in terms of future based on the different climatic projections. So as you can see that the dry days in the most areas, you can see that the dry days are increasing and the wet days are decreasing. So like in the monsoon season, we are going to get less rainfall, and in the summer, and this will accelerate the I mean the drought conditions, especially in the monsoon seasons. And in the monsoon seasons, we are going to get the less wet days. Okay, and but the more intense rainfall will be triggered. So here you can see that the higher amount of the rainfall events are increasing, especially in the mountainous region and in these regions. And this is the historical scenario, and these are the future scenarios like 2006 to 2100. So how these changes are happening, that you can analyze. So like dry days will be more, especially in this region, and the wet days will be more, especially in these regions. So most of the patterns are similar in different models. So this will be predicted through different models. So all these actually all these analysis is saying that if the temperature rise will be more in the future, so there will be number of negative consequences will be there in terms of precipitation, extremity, either you can say the intensity wise or you can say the frequency wise. So similarly, we have also worked on the different drought conditions. So how the drought will be occurred in the India if you assume the temperature increase with respect to different climate model scenarios like IPCC assessment report 5 based climate projections. So here you can see that different RCP based scenarios are showing. So this is historical. So we have calculated the SPI index for calculating the droughts. So these are the historical scenarios, and this is the scenarios that we have calculated for the future times based on the RCP 4.5. So this is moderate level emission scenarios, and if based on this RCP 4.5, we can assume that like the temperature will rise around 1.5 to 2 degrees centigrade. So if this much rise will be there in terms of temperature increase, so in this area we can see that a clear change in the drought conditions. So you can see that in this area, especially in the central India and the southern India, and in the western portion of the India, we will have more drought conditions. But if you consider the extreme high emission scenario like RCP 8.5, so according to RCP 8.5, the temperature can rise up to like greater than 4 degrees centigrade. And if that kind of temperature rise will be there in the future, so you can assume how the drought conditions will be there across India. So I think except in few areas, especially in the Himalayan areas, in Jammu and Kashmir and Ladakh regions or some northeastern areas and western Ghat, if you leave out all these areas, so other portions in India will face the different drought categories. And here you can see the drought index, and 1 to 1.5, this is the least drought index, and 3.5 to 4. So most of the category will fall in the extreme high drought conditions. So all these consequences will be there if we talk about the temperature changes, and there will be some changes in the precipitation. So these are the notified changes that we have already seen in different regions of the India. Might be if you consider the whole India, okay, so there will be less intense observations you will get, but at regional scale or at local scale, the intensity or will be more, or the observations will be more intense. Okay, so these are the observations that we have notified through the different climate model data sets or the historical records. So now I would like to talk on the real-time study that we have performed at NIH, and based on the different climate projections and different LULC based change conditions, how the climate change is affecting that we have observed in some areas in the northeastern India, and how the observations are there, how the water availability will be changed, and what will be the consequences of climate change and land use, land cover changes in terms of water availability, water demands and supply, and then how the basins will be resilient, or how the regions will be resilient to adopt these climatic changes that we have also analyzed, and what would be the mitigation policies or strategies, and what could be the adaptation policies or strategies that we will discuss in the coming slide. So here now I am going to present you one very good study that we have conducted at NIH, and here in this basically project we have done like long-term hydrological assessment for the development of water security plan in the Mizoram state. So Mizoram is the part of northeastern states, and in Mizoram we have a great Himalayan ranges, and we can say the newly Himalayan range, and the elevation goes up to like from 1000 meter to 3000 meter in the Mizoram. And Mizoram is abundant of the water resources because northeastern regions considered as a highest wettest area in the world. As we know that in some areas of the northeastern states, we get the higher amount of the rainfall. If you consider the average annual rainfall, so it varies like from 1000 to more than 6000 annual rainfall. So northeastern region receives throughout the year a good amount of the rainfall, but we have also observed the negative consequences of the climate changes, or we can say that the negative consequences of the land use land cover changes. And how these two factors, like one factor we can consider the climate based changes, and in one factor we can consider the land use land cover based changes. So how both the things are together happening in the state, and if you consider these factors together, so what would be the negative consequences in terms of water resources in the particular region or particular state, that we have analyzed here. So this is the background of the study. So Mizoram is a state with abundant water resources, and in Mizoram, basically what we have done here, we have considered the Mizoram state and along with the neighboring areas. So basically in the Mizoram, we are getting three kind of river systems. One is the Bangladesh, minor rivers draining into Bangladesh, then minor rivers draining into Myanmar, because Mizoram is also connected with the Bangladesh and Myanmar. And one is major river basin, that is Barak, that is also the part of the Mizoram. So these three river basins are there in that particular state, and how these basins are affecting in terms of water availability, demand, supply, and all that we will see. So it is obvious that due to the effect of climate change and land use change, the problem of water scarcity and water management may increase in the coming times. So that we have analyzed and targeted to solve all these issues while performing a detailed study. So I would like to show you all the results here also. So keeping these factors in mind, the proposed study aims to performing long-term hydrological assessment for the development of the water security plan. So as we know that there are issues are there from the climate change side or the land use land cover change side. So ultimately our aim was to manage the present hydrological water availability in the state, and how we can make sure for the future water security in the state. So because of that, we have considered both the factors, like the climate change factor from the climatic driven parameters, and the LULC based changes that is mostly driven by the increasing population size as well as the settlement in the state. So the ultimate objective of this study is to construct and perform the advanced modeling framework to analyze the long-term variability in the water resource components like water availability and demand. So that we have analyzed with the possible threshold of resilience. So here we have also computed how these uh, regions, or how the areas in the particular state, how the areas or how the we have considered the district wise scenarios, also we have considered the block wise scenarios, also we have considered the sub basins also. So how areas are able to adopt the LULC changes and climate change in terms of resilience, that we have also analyzed. And then how we can manage the water use efficiency and maintaining the adequate water supply for the sustainable development of water resources, that we have analyzed in this study. So if you see the study area, so this is the study area. So this is actually the boundary of the Mizoram state. Along with this, some portion of the Assam and some portion of the Manipur that we have also included in this study. So this is the whole study area that we have taken. And if you see, three river basins are there, and so three major sub-basins are there, and further we have divided the whole study basin into number of sub-basins to further analyze the hydrological in terms of water balance, in terms of hydrological projections, to make the process more dynamic, I mean at more local level. So if you see, the average annual rainfall varies, like in this particular study area, like 200 mm to 6400 mm, and the average annual temperature here it is recorded around 21.6 degrees centigrade. So here temperature is not varying that much, but you will see that there is a strong variations in the rainfall. Like in some areas we are getting around 1200 mm, but in some areas we are getting 6400 mm average annual rainfall. And the elevation is also varying, like from 18 meter to 3000 meter in the areas. So this is the methodology. So in this study, what we have done, so that I have listed out here different components that we have studied in this particular project. So one is the generation of improved rainfall data set. So as you know that in the Himalayan areas, we have very limited availability of the rainfall gauges. So the problem is that when you will start working on any particular river basin or sub basin, so generally you will be lacking of the good amount of the data. So if you don't have the good amount of the data, your analysis will not be that much accurate, or your results will be produce more uncertainty. So you cannot be sure on the modeling outcomes, or we can say the results of the study. So to avoid the uncertainty or errors in our modeling outcomes, to be more precise in terms of calculating water availability, demand and supply, all these conditions, we have tried to generate our own approach, and based on that we have generated an newly gridded rainfall dataset for this particular study area, so that we can minimize the errors and we can produce more reliable results. So that was the first thing that we have done. Then we have also performed the rainfall trends and change analysis to analyze the impact of climate change within the state. I mean, how the temperature is going to affect the rainfall pattern in the state, in terms of rainfall amount, in terms of rainfall seasonality, in terms of rainfall frequency, in terms of rainfall intensity. So until and unless if we don't know how the rainfall is affecting, I mean how the rainfall is varying in the particular study area, so we cannot go for the further analysis. So because of that, first we have analyzed how the climate change is going to affect in terms of rainfall, and the change analysis we have performed here. Then number of data inputs are actually required to develop this framework. And in this particular study, we have used number of field-based measurements, number of modeling tools we have used, and some conceptual or empirical equation-based modeling tools we have developed. And then we have integrated all these frameworks together. So number of data sets were required actually to perform this study, so that we have processed. So then the primary step, we have developed the hydrological model. So we have used the SWOT model for this purpose, and different hydrological scenarios we have generated. The prime objective was to manage the water to make the water security plan, as well as to make the sustainable developmental water resource integrated management plan for this state. So first we had to have the hydrological scenarios for this analysis. So we have used the SWOT model, and we have generated the number of hydrological scenarios. So in the historical time, we have used the observed data that we have developed at our institute, as well as we have got some data from the different nodal agencies like Central Water Commission, IMD for rainfall data, and Central Water Commission for the discharge data to simulate the model and to calibrate and validate all the modeling things. So ultimately, we have generated the hydrological scenarios, and we have used for this purpose, we have used the climate model data set. For the historical time, basically we have used the observed data, and for the future times, we have used the climate model data sets to analyze the impact of the climate change. First, in terms of rainfall, as rainfall was taken as the primary input to driven these hydrological processes, and then based on that we have tried to perform the assessment of the different hydrological components like water availability, demand, and water availability, demand, and supply conditions within the state to different climate model data sets. So that we have done. So of course, we have performed the hydrological calibration, modeling, and optimization of model parameters. Then hydrological assessment under LULC changes. So as I have already informed that we have considered two factors here. One is the climate factor that is based on the climate model data sets from the IPCC climate model data sets. And the second thing is that we have considered the land use land cover based changes. So for this purpose, we have used the historical land use land cover maps. So for the historical land use land cover maps, we have generated our own through the processing of the satellite data sets. And for the future times, we have projected the land use land cover map using the machine learning approaches like support vector regression and random forest algorithms. So based on that, we have projected the future land use land cover maps, how the land use land cover was there in the historical time, and how the different land use classes are going to change in the future, so that we can incorporate all these changes in the hydrological model, and then we can analyze the impact of these changes in terms of the hydrological scenarios, like how the water availability will be changed, how the water demand will be changed, as the land use will be changed in the historical time and in the future time. So that we have done here. Then we have performed the hydrological assessment using the climate change or climate model scenarios. So different water availability, demand, and supply scenarios were generated, and then we have performed the change analysis. I mean, how these scenarios were there in the historical times, and how the scenarios will be going to change in the future times, especially in the near term and far term. So both the things we have done. Then we have implemented here the BVCOEW framework for the hydrological resilience analysis. So BVCOEW framework is a very good tool that actually depends on the different water limit conditions and energy limit conditions. And based on that, we have calculated the dryness index and evaporative index to analyze how these climate and LULC changes are going to affect the basin's water availability, or the state's water availability, and what and how many regions are going to adopt this climate change, and how many basins will be failed to adopt this change in terms of resilience. So that we have analyzed, and after that we have produced the recommendations for mitigating climate change impact and adaptation policies. So based on the analyzing of the different observations that we have got in this analysis, so how best we can make the mitigation management plans, and what could be the best adaptation policies, so that in the future and in the current time we can enhance the water security within the state. So all these things we have done in this study. So I would like to show you the results and the observations one by one, so that you can easily understand, I mean, how this climate change is going to affect the region's water availability, water demand, and how the climate change is going to affect all these things, as well as the land use change, and how best we can manage all these resources. So as I have talked on for this study, we have generated and we have analyzed the different rainfall data sets, and we have generated our own data sets because we compared the different available rainfall data sets. Like here we have considered the IMD rainfall data set also, and also the satellite-based different rainfall data products. But we did not find any good rainfall data set that can actually represent the actual rainfall pattern within the state in terms of seasonality extremity. So because of that limitations, we have generated our own data, and here you can see that this is the product that we have actually generated for this state. So this data set we have used finally. And we have also performed how the climate changes are there in that in particular state and the historical time, or how the changes will be there in the future time based on the climate model projections that we have analyzed. So here I have shown you the changes in the mean rainfall in the selected study region, and here you can see that near versus far term changes. So here we have considered historical period, then uh, some future time period we have selected from different experimental scenarios of the latest climate model dataset like SSP 245 and SSP 585. And for this time period and this time period, we have analyzed all these data set to see how the mean rainfall is going to change in the state. So here you can see that different levels of changes are highlighted here. And if you see any spots in the green color or blue color, that is actually representing the basically decrease in the rainfall, mean annual average rainfall. And here you can see that all these regions are going to decrease in the rainfall, and some areas we are going to some amount of the increase in the rainfall. So this is happening in the state in terms of mean rainfall. And similarly, we have also analyzed the dry spell frequency and wet spell frequency. I mean, we wanted to know that, I mean, how the dryness will be there in terms of temperature increase, how the rainfall will be changed in the state in terms of wet spell and dry spells. So that we have analyzed. So this is the SWOT modeling results. So basically, this is our whole study river basin. So in the green color, I have highlighted you the Mizoram state. So basically, we have focused on the Mizoram state. But as you know that if you want to perform the hydrological analysis, you have to go with the hydrological boundary concept. You have to consider the hydrological boundary. We cannot analyze the state boundary in a hydrological analysis. So this region will be selected for the whole entire analysis, and the whole study region we have divided into further sub-basins to analyze a local level changes in terms of different runoff components. Like here you can see that we have considered the rainfall, surface runoff, lateral flow, water yield, sediment yield, ET and PET. So all the water balance component are shown here, and this is the water balance of this particular study region. So that we have computed through SWOT model. And if you see that the precipitation is coming around 1900 mm. I mean, in the particular Mizoram state only. Here we have shown you the result on this particular green line boundary. And the surface runoff around it is coming 486 mm, and if you see the ET is coming around 709, and the total water yield if you see, so it is coming around 1100 mm. So these are the some average annual water balance components. And these are some modeling parameters that we have optimized for the model calibration and validation purpose. So different hydrological parameters were selected, and these are the parameters which we found that these are the most influencing modeling parameters for the simulation, hydrological simulation process during model calibration and validation. So these are some ranges that we have selected for the entire simulation, and these are the fitted values, the final values after doing the calibration and validation. And here, this is the rainfall runoff ratio is showing. So the actually the standard rainfall runoff ratio should fall between the range of 0.4 to 0.8. So this is the rainfall runoff ratio standard range. So if you see any region below this 0.4 range, so that means these areas can be considered as a dry areas where the rainfall is not converting in terms of runoff. And here, if you see any areas which are showing more than 0.8, so those areas can be considered as the wet regions. I mean, whatever the rainfall is coming, mostly rainfall is converting in terms of the runoff. So here, if you see in this area, so most of the region is falling within this range, like 0.4 to 0.8. So in this area, you can see that the more runoff is there. And in this area, basically, you can see the less runoff is there as compared to this area. And you know that in this area, the rainfall is average annual rainfall is more than this area. Because if you see the overall average annual rainfall, so it is coming around 6,000 mm. But if you consider only the Mizoram, so it is coming around like 2,000 mm. So this is why here the runoff rainfall runoff ratio is less as compared to this area. So these are some observed gauge locations were considered for the model calibration and validation. So we have applied like SUFI2 optimization algorithm in SWOT model for doing the calibration and validation. So these are the results. And these are the final performance evaluation statistics, like some R square and NSE at different gauges. So how the model is calibrated and validated, that is showing the modeling strength. So here, if you see the distribution of the different rainfall components, so basically here I have shown you most influencing component that can affect the water availability within the state. One is the ET. So ET is the loss from the system, if you consider the hydrological system. So soil moisture is the part of the hydrological system, then water yield and groundwater. So water availability, if you consider the water availability, how much water availability is there and how much demand is there. So ET is the demand side. So ET is the loss, or we can say the demand within the state, and soil moisture and groundwater and the runoff, if you will add, so total water yield you will get. So as we have already seen that this region is having more water yield than this region, but the ET demand is here, it is very higher in this area. So this could be one of the reason that the water availability is less as compared to this area. And here also that the soil moisture is more, but parallelly the ET demand is very high. So, and the groundwater component is also high here. That is why the total water yield contribution, you can see that higher in this area. So this is the overall water balance in the state, and how the hydrological components vary across the study area. So this can show some of the variability in terms of the different areas within that particular study region, how the hydrological scenarios vary within this region. So now I can show you how the land use changes happened in the state, I mean in the study region. So red color boundary showing the Mizoram state, and rest of the boundary is showing the total hydrological boundary that is considered for the analysis. So if you see here, uh, so uh, uh, so uh, you can see the different land use land cover change scenarios, like we have considered for 1985 land use land cover map, and here we have considered 1995, 2005, 2020, 2050, and 2090. So these are the projected land use land cover map. So if you see the land use land cover area, like we have divided the whole study area into different land use classes, like forest land, agricultural land, urbanized, settlement, barren land, shrubs, and water. So most of the study area is dominated with the dense forest land that is coming around, if you consider the 1985. So it was around 89.24 percentage of the total study area that is coming as a forest land. And the agricultural land is like 9.4 percentage of the total area, and similarly for the other classes. And how this is going to change in the future, that you can see that if you see that 1985 to 2090, or we can say the current time period, latest current time period, so 2020 map, so you can see that around 4 percent reduction we have observed in the forest land, and the agricultural land is increased. Similarly, the urbanized settlement is increased, and similarly, the barren shrubs and the water body is decreased. So if I will show you here, like you can see that the dense forest land has been reduced, and similarly the agricultural land expansion is there in that particular state, and the settlement expansion is there, and the barren land expansion is there, but the shrubs and waters are reduced. So most of these classes are showing some classes. I mean, the mostly the agricultural land and urban settlement expansion and reduction in the forest land and barren land are there. So some significant change is there if you consider, and this will be more happening if you consider the 2090 scenario. Like here, the forest area was around 89 percent, and here if you see that, so it will be there around 81% only. So significant reduction will be there in the future as per the projected land use land cover conditions. And because of that, definitely there will be a strong variability you will find if you will analyze. So there will be a strong variability in terms of the water availability and water demand and supply and all these conditions. So how these LULC changes have affected the state's water resource availability and demand that we have calculated. And here you can see that the differences in the ET at sub-basin wise. Like I have told that the whole study basin was divided into number of sub-basins, and each sub-basin, if you can see, so around percentage of change, if you see that, so percentage of change is increasing here. In the red color, most of the basins here you can see that, so 0 to 40% change is there. So that means these LULC is significantly going to affect the runoff in that particular basin or ET conditions in the basin. So because of the reduction in the forest cover and expansion in the agricultural land or urbanized settlement, you can see that the significant increase in the significant increase in the ET, evapotranspiration component, you can see across the basins. And in this area, you will see that the more dense red dots are showing the higher ET changes as compared to this area. So this area is more prominent for the ET changes in terms of LULC change. So under different LULC conditions, like here you can see that here we have calculated the scenario 1985 versus 2020. So hardly you will find any kind of change. Then if you consider 1985 to 2050, so in some areas you will find some decrease, and in this area some areas are showing increase. But here in this case, if you see, consider the land use land cover condition changes like 1985 versus 2090. So most of the subbasins, you can say, or most of the area within the Mizoram state, we can say, is showing the changes in the evapotranspiration demand. Similarly, for the water yield, we have also calculated like 1985 versus 2020 land use land cover change, and similarly for the 1985 versus 2050 and 1985 versus 2090. So here you can see that the water yield is mostly showing the decrease and increase, a mixed response. Here you can see that, like here in this area particularly. In this area, this color is coming like up to 20% reduction, especially in this area you can see like from -5 to -20%. So in this area, basically we are going to reduce the water yield. Here also, if you consider the near-term changes like 1985 versus 2050, so up to 10% changes, -10% reduction in the water yield you can see. And here in this area, some increase you can see, like here in this area, basically. So this is a high rainfall area we can consider. So, but this area is mostly affecting in terms of changes in the water yield. So, in the similar way, we have analyzed the effect of the climate change in terms of CMIP 6 climate models. Like we have considered here two models, like access model and uh, uh, EC Earth model, but here I have included the result only of the access model under different experimental scenarios. So here we have considered two experimental scenario. One is SSP 245, another one is SSP 585. So SSP 245 represents the moderate level changes, and SSP 585 is showing the extreme high emission scenario based changes. So in this, you can see that this is the average precipitation, this is the average ET, and this is the average water yield. So here all the three main components are analyzed. So here you can see that the average precipitation, you can see the response in terms of like 2022 to 2050. So decadal analysis we have performed, like here you can see all the results from the near term based changes like 2022 2050, and here you can see the changes in the far future times like 2062 to 2090. So in terms of precipitation, if you see from 2020 to 2050. So most of the areas are showing the reduction in the precipitation, especially in this area. And in this area, you can see some increase in the rainfall amount. So rainfall variability is also there. Like even in this small, even in this area, like northeastern area, here we have considered mainly the Mizoram state. Even in this small scale basin, we can see that lot of spatial variability is there, like in terms of rainfall. So in now you see the ET based changes. So that is also highlighting here. So most of the bases are showing the increase in the ET demand. So in the green color is highlighting the increase and the blue color is highlighting the decrease. So in here in this particular ET, you can see that uh, the increase in the ET demand, and this ET demand is increasing because of the increasing temperature. So that can be directly correlated, like if the temperature will be increased, so definitely the ET demand will be more and more. Okay, so here you can see, and in terms of water yield, so mixed response. Earlier we have seen in terms of LULC based changes, and in terms of like climate changes also, we can see that a mixed response in some catchments or in some subbasins, we can see that there is a increase in the water yield and maybe in some areas we are seeing the decrease in the water yield. So the reason could be like decreasing the water yield, maybe reduction in the rainfall in this area. Okay, and the increase in the water yield may be because of the intense rainfall, because here you can see that the rainfall is increasing side in this area. So this is why in this area we are seeing the more water yield in this area. But if you see the late time scenarios, like in the far term scenarios like 2062 to 2090, a slight recovery is there. I mean, here you can see that in the most of the basins in this area, we are going to more water yield in this area, and we are going to more ET in this area, and we are going to more rainfall in this area. So slight recovery is also there. And similarly, for the extreme emission scenario, So these scenarios are based on the SSP 245 and these scenarios are based on the 585. So if you consider the high extreme emission scenarios, so these changes will be accelerated here. Now, if you see the population of the Mizoram state, so if you see that there is an exponential increase, you will see that in the terms of population in the Mizoram state. I mean, here you can see that after 1981, if you see that there is a clear increase, a, a clear increase in the population. So if you see that in 1961, the population was like this. Around 2 lakhs, and now it is increased in crores in 2021. So if the population will be increases in the future time in that particular region or state, so definitely the water demand will be high, but the water availability issue will be there, and the water is not going to change in terms of amount. Okay, but the variability is there. So if there will be negative consequences of the climate change or LULC based changes, so we have seen that based on the analyzed observations, we have seen that the ET is going to increase. That means more loss in the system. So definitely this will reduce the water yield in the future, and the water demand will be increasing. So definitely there will be some negative consequences will be there. So here I have shown you the total demand and total supply in the state. So if you see as per the SSP 245 and SSP 585, so here you can see that in the historical time, mostly the total demand is meeting the supply conditions. But in near terms, there is a slight variations you can observe here. Okay, but in the far terms, the variations will be more. So this is what we have observed here. I mean, if the climate variability will be more, okay, so demand and supply gap will be more. But as far as if you consider the near terms like up to 2050, so we are able to meet the total demand because this region is already abundant of the water resources. Okay, so it will meet the total demand within the state. I mean up to 2050. But if you consider the far term changes, so definitely this gap will be there. So that water we have to conserve, or we have to make the water conservation guidelines, or we have to minimize the climate change impact in the state, or we have to make the adaptation policies so that we can minimize this particular gap. And here we have divided the total demand in terms of irrigation water demand and as well as the domestic water demand. So here I have shown you the scenario of the irrigation demand. So irrigation demand, if you see that in the historical time, it is meeting, and in the 2050, I mean, there is a slight gap in the irrigation demand. So that means that we have already seen in the case of LULC based maps. So that you have seen that there is a huge not huge, but we can say the moderate level expansion was there up to 2050 map in terms of the agricultural areas. So the agricultural area will be extended, and I mean the population is going to increase, so definitely the water demand will be more, but the water availability as well as the water availability is getting less because of the negative consequences of the climate change issues. So the irrigation demand will be more because of the increasing population as well as the agricultural expansions, and similarly, therefore the supply will be less. So there is a clear gap you can see, and this gap in the far future time will be more if you consider the 585 or 245. So in the near sorry, in the far future time, this gap will be more. And this is the domestic water demand. So domestic water demand, like here up to 2050, in terms of domestic water demand also, if you see in the domestic water demand up to 2050, we are able to meet the conditions, okay, as per the availability of the water within the state and neighboring areas. And in the far future times, you can see that the demand will be more, domestic water will be more, demand will be more, and it is exponentially rising because of the increasing population. And similarly, the demand and supply will be varying because of the increasing gaps. So this could be the problem in the future. And here we have compared the unmet demands. Like here we have shown the irrigation demand in the historical near future and far future. And this shows the unmet irrigation demand here. So in like we have already seen that, in the historical time, we were met the conditions in the near term scenarios. We are able to almost meet the irrigation supply as well as the domestic water supply. But in the far future times, this gap will be more. So this variation you can see here. So similarly, we have also analyzed the Budico base curves. So basically, it deals with the water energy limit conditions and uh, based on the different factors like dryness index and evaporative index. So evaporative index, if you see this particular curve, uh, if you see this particular curve, so you can easily understand the concept of Budaico. So here, this is the theoretical Budaico curve, and these red dots are showing the average conditions of the different components. Like here, we have considered mainly three components. One is actual ET, one is PET, and one is total available rainfall within the sub-basins level. So these are the sub-basins within the selected study area. So this is the theoretical Budaico curve. If any point will fall on this line, so that means there will be no gap between the water limit conditions or energy limit conditions. And actually, theoretically, all the points, it should fall in this particular line. If all the points will follow this particular line, so that means there is no consequences of the climate change or land use changes on the these different water components like ET, PET, and P. So here in the y-axis, we have shown you the evaporative index that is calculated by the actual ET divided by the rainfall. And here in the x-axis, we have shown you the dryness index that can be calculated by the potential ET divided by the rainfall. So if the potential ET, if the rainfall and potential ET ratio will be more than 1, so that means that basin will move towards the dryness conditions. Okay, so similarly in the evaporative index, if any point will be more in this particular one aspect, like here the range is 0.0 to 1. If any point will fall this particular line in this line, so that points will be considered as the energy limit condition, and here it is water limit condition. So that means these basins are able to sustain the climate and uh, land use land cover changes conditions in the future as per the different historical records or whatever the data we have used. And if the basins crosses this particular line, this line, this dotted line, so that means those basins are moving towards the dryness conditions. That means these basins are not the resilient in terms of the water. So, so here on these particular factor, we can calculate how many basins are able to adopt the climatic and land use land cover changes in terms of ET, in terms of PET, and in terms of rainfall. So here different climate models we have used like Access model and EC Earth model. So these are two models we were considered for this particular analysis, and here different near terms and far term scenarios we have calculated. So here you can see that in these points, the points which are coming here in this particular sections. So these are the energy limit conditions, or they are able to capture the, they are able to adopt the climatic conditions and land use land change conditions. But if you see the points like here, so these are the basins, or these are the points. They are not able to adopt the climatic changes or land use land cover changes, and these are falling as a non-resilient subbasins. We can categorize into non-resilient areas or non-resilient subbasins. So, and these points which are showing here and here, so these are very far from this theoretical Budako curve. So that means these subbasins are more critical. So if the temperature extremity or land use land cover changes are more in the particular state, in the particular region. So these points will go more far from this theoretical Budako curve, and those basins will face more severe climatic change conditions, or the negative consequences of the climate change. And these basins can be categorized as the non-resilient basins. That means these basins will not be able to adopt the changes in terms of LULC changes and climate changes. So those analysis we have done, and here we have categorized the different models under different models in the far future terms and near future terms, how many basins are found not resilient. So if you see that in different models, we can see that mostly 3 to 5 subbasins are found not resilient. So out of 105 subbasins, around 30 to 35 subbasins were found not resilient. Based on this Budako analysis, that means these subbasins will not be able to adopt the changes like climate changes and land use land cover changes within the state. So that means we have to be more we have to give more emphasis on these particular basins in terms of managing the water availability conditions and water demand conditions. And here I have shown you the basins which are computed as the surplus water surplus regions or water deficit regions. So here you can see that these red color points are showing the water water deficit conditions, and the green color points are showing the water deficit conditions. So in these red regions, you can see that these basins will be water deficit conditions, will fall under the water deficit conditions, and these red color points will fall under the water surplus conditions. So in this particular area, if you see that in this particular area, most of the basins are found water deficit conditions in the future time, as per the computed by the different climate model scenarios. So this is the computed total in terms of amount, what amount of the water surplus will be there and what amount the water deficit will be there. So you can see that the water deficit conditions are increasing, as well as the water surplus condition in also increasing, as in some basins like here you can see that, because in this area we are getting more water yield or more rainfall, so water surplus conditions are increasing, and here we are getting more water deficit conditions. So there is a clear deviation. You can see that within the particular state, in this area we are getting more deficit conditions, and in this area we are getting the water surplus conditions. So we have to give more emphasis on this particular subbasins which are found water deficit subbasins. So these are some conclusions I am not going to read. I have already discussed here. But what could be the mitigation guidelines by the IPCC as per the AR6 that we have to follow? So they have suggested some guidelines so that we can manage all these negative consequences of the climate change, and how we can how we can go way forward with all these consequences. So like we have to accelerate the renewable energy deployment. Like we should promote for the renewable energy resources like solar, wind, and hydroelectric energy to phase out fossil fuels. Because if you will burn more fossil fuels, so there will be more adding carbon in the atmosphere, and this will increase more heat in the atmosphere, and the radio forcing level and the temperature will go more rise. So afforestation and reforestation, we should go for it. And like we should promote for the afforestation, especially in the barren lands, and we should go for the reforestation, protect and expand forests to enhance the carbon capture. So sustainable agriculture, we should talk about the sustainable agriculture, like adopt practices like no-till farming, agroforestry, and crop rotation to reduce emissions and enhance soil carbon storage. Then we have to mainly emphasize on the reduced methane emissions. Methane is a gas which can lead to the global warming, or we can say the radiative forcing level. That is the main cause of the increasing temperature. So address methane from agriculture, waste, and fossil fuel extractions through improved practices and technologies. Then low carbon cities promote compact, energy efficient urban planning with accessible public transportation. So these are some standard policy guidelines suggested by the IPCC AR6, and on these conditions we have already done the Paris Agreement, and India is also following all these things. So and as per the IPCC assessment report 6, if you see the adaptation policies, so they have praised the Indian government, like we have a lot of cut down the carbon emission. But based on this study, we have concluded that I mean, how we can manage the Mizoram's water resource security plan based on the available observations. Like we have seen that the temperature is going to increase, the rainfall variability is increasing, I mean the land use, land cover change conditions are also going to affect the water availability, demand, and supply conditions. And we have also seen that through the climate projections, like water availability in most of the regions are going to reduce, and in some regions we are going to get higher water yields, but the causes are different. So these are some adaptation strategies that we can follow, so we can manage more on the water security side, like enhance rainwater harvesting. So we should install systems in both the urban and rural areas, where like we have also seen that in some of the regions we have the water deficit conditions. So in that particular conditions, you can perform the similar study, and you can enhance the rainwater harvesting kind of things. Then protect and restore forest. So in areas where we can see that the agriculture expansion is there, settlement expansion is there, or where the forest reduction is there, so there we can go for the reforestation or afforestation kind of things. Then efficient irrigation practices, like we have clearly seen that the irrigation water demand is going to increase, and the supply demand and supply gap will be increasing in the coming times. So to manage all the things, we should go for the water efficient technologies like drip and sprinkler irrigation to reduce water demand, especially in the agriculture side. Then groundwater recharge initiative, we have to go for it. Like develop recharge wells and check dams, like where we have seen that these are the regions where we are going to water deficit conditions, or the subbasins we have classified as a non-resilient water subbasins. So in that particular subbasins, we have to promote more check dams, or to store more waters, and we should promote some structures that can we can enhance the groundwater recharge. And domestic water conservations, like we have also seen that due to increasing the exponentially, like the population is going to increase. I mean, In the similar way, the other Indian states or other Indian cities are also going to see the exponential growth in terms of water, and the but water is limited, so we have to go for the domestic water conservation, because the definitely in the future the water demand will be more. Okay, so we should go for the public awareness campaigns, and we should promote the most reliable water conservation things, so that the per availability, the consumption of the water can be enhanced. So long-term adaptation plans could be there, like climate resilient infrastructure, like we have identified some basins which are found non-resilient sub-basins. So in that particular basins, we can promote the climate resilient infrastructure. Okay, some long-term dams, check dams, or reservoirs or barrages kind of things we can promote, so that the more water can be conserved. Okay, and integrated water management plan is more important. Based on the different observations, like we have seen here in this study, and this can be promoted by the state itself, because in India, state is the nodal for the managing the state level water resources. So a state level water resources management plans can be made by identifying different land use, land cover change based conditions, and how the population is going to increase in the particular region or state. So all these things can be analyzed, and based on that, an integrated water management plan can be proposed. Then early warning and monitoring systems can be developed, like in most of the cities, especially in the last few years, we have seen that many cities have faced the severe flood conditions. Alongside, in some cities, we have seen that many drought conditions. So some kind of early warning system and monitoring system kind of things we should develop, so that these kind of extreme events can be handled, or we can aware about the public to all these negative consequences, and we can add and to make the public proactive decision making. Then sustainable land use, land cover things can be promoted to enhance the hydrological significance of the region by reducing the impact of climate change and other changes like land use, land cover changes, like we have seen the agricultural expansions or urban expansions. Then community-based water governance is another concept that we can adopt, like involve local communities in managing and conserving water resources, ensuring equitable distribution and sustainable practices across different sectors. So some cross-cutting recommendations we have also recommended to the state, like integrated policies, like inter-ministries kind of things, like Ministry of Water Resources can be only emphasized on the water-related things, but Ministry of Environment and Climate Change is mostly governing the making the policies about the consequences of the climate change. So inter-ministerial, policies should be made, so that all these things can be managed. Then some equity and justice, like things are there, like prioritize vulnerable communities and ensure equitable access to resource, technologies, and opportunities. Then global cooperation is also needed. Then innovative financing. I mean, if you think that we should go for the mobilized resources, like for climate action through green bonds, carbon markets, and international climate funds like Green Climate Fund. So we should go for that, so that more fund, like World Bank provide number of funds, for the developing countries. Okay, so those opportunities we should grab, and we can enhance our infrastructure in this direction. So we can enhance the mitigation kind of things in the India. So I think time is up. So I should stop my presentation here, and I'm going to close my presentation. So
Thank you so much, sir, for such an enlightening session on mitigation and adaptation strategies for climate change scenarios. Now, I request the participants, if they have any queries, they can ask.
if
All the
you if
participants are requested.
yeah,
If
please
anyone
ask
has
your
any
queries,
question,
or if you have any suggestions or comments, so please, you are most welcome.
all the participants, if you have any question, you can ask.
I think they are muted.
Uh, they can raise their hand if anyone
Okay.
has any doubt.
Participants, any question?
Hello,
Sir,
sir.
I have one. Yes. Yes,
Hello,
ma'am.
good evening, sir. Yeah, I'm Dr. Vijaya Pawar from Bharati Vidyapit. It's very nice presentation. Only one question that I'm having is from where we will get the data related to water consumption, potable water consumption in a particular city.
You can, as like we have contacted our Mizoram State Irrigation and Water Resource Department, and we have also, while doing this project, we have coordinated with the state chief engineer as well as the other engineers there, and they were the member of this project also. So all these data set we have got from there.
Okay, thank you, sir.
They also they also publish annual reports also. If you refer the state annual plan action plan, every state publish their annual year action plan. So in that you can also get all these kind of data sets so that you can refer to that.
Thank you, sir.
Good
Next.
evening, sir. Myself, Vinaya Kulkarni. I want to ask one question. So, what would be the most effective strategy to mitigate climate change within India? Is there any strategy that could be effective all over India?
Yeah, definitely. I would like to comment on this, and as I have shown you number of things like if you are talking about the managing Himalayan water resources, so definitely there will be different strategies. If you are concerned about the water sustainable water development plans, water security plans, water availability, so a number of things are there. Like if we are focusing on the extreme event, like if we talk about the Himalayan areas, so we are more concerned about the extreme events. Okay, and we have seen that number of globe events happened in the past, and most of the Himalayan glacial lakes are vulnerable to globe events. So we are trying to develop some early warning kind of systems. Then if we see the agricultural sector, so like in some areas we are going to get more agricultural expansions because of the increasing populations. But the water limitation conditions are there because in some areas we are seeing that the total amount of the rainfall will be decreasing in the future times. So definitely the water availability will be the issue. So how we can promote the sustainable agricultural water management? So we have to go for the like advanced irrigation techniques, like we should enhance the irrigation efficiency while using while using the sprinkler based systems, or we should go for the alternative crops like based on the different water conditions, so that we can analyze. Then like here in the Mizoram state, I can give you the best example. So in one area we can see that the water deficit conditions. In other areas we can see the water surplus conditions are there. And we have assumed in future in one area, we are getting the more water in one area, we are going to get the less water in terms of the water availability. But the demand is increasing because of the increasing population within the state. So how we can manage both the areas within one state? So we can divert, we can make the interlinking kind of things, and we can divert the water from one region to another region. So in this way, we can go for the management plans. And definitely the major plan is like we have to go for the alternate renewable energy resources. We should reduce the carbon emissions. We should cut down the carbon emissions. We should promote the sustainable things.
Thank you, sir. Thank you so much.
Hello,
Uh,
sir.
Yeah.
One more question.
Ji.
Sir, if you have presented or demonstrated everything with respect to graphs, so which tool you have used in order to get these graphs?
Like here we have analyzed all these things in some modeling tools we have used for analyzing the hydrological scenarios. We have used the SWOT model, that is the hydrological model that we use. And for the computation of the water availability and demand, like you have seen. So for that we have used the WEEP model. And for Budaco analysis, we have used the empirical equations, and that we have coded in the Python environment. So all these things we have used.
Thank you, sir.
And for some generating some data inputs like the land use, land cover maps and all that, that we have used the satellite data sets that we have procured, and using some GIS tools like QGIS and ArcGIS to process all these things.
Thank you, sir.
Thank you, sir. Thank you so much. So if there are no more questions, I would like to conclude the session. So on behalf of Bharati Vidyapeeth's College of Engineering for Women Pune, I extend my heartfelt gratitude to our esteemed speaker, Dr. Vishal Singh sir, for delivering such a thought-provoking and enlightening session. Your expertise and insights have been truly valuable for all of us, sir. I also thank all the participants for their active engagement, enthusiasm, and cooperation throughout the session. I request all participants to kindly remain in the meeting. The next session is going to start shortly. Thank you so much.
Thank you, madam. Thank you all.
Vidya ma'am.
Yes, yes. So,
Yeah. We can start. Sir is there.
okay, ma'am. So it's my honor to introduce our today's esteemed speaker, Dr. Vijay Kanavade, sir. Dr. Vijay Kanavade began his academic journey with Master of Science in Physics from Fergusson College, Pune in 2002. Following this, he pursued a Master of Technology in Atmospheric Physics from the Department of Atmospheric and Space Sciences at Savitribai Phule, Pune University in 2004. In 2010, Dr. Kanavde's academic progress earned him the prestigious Marie Curie Research Fellowship, which took him to the University of Leicester, UK, for his doctoral studies. His research focused on satellite remote sensing of carbon monoxide in the lowermost troposphere, a critical study for understanding the atmospheric composition. After completing his PhD, Dr. Kanavade continued to contribute to cutting-edge research as a postdoctoral researcher at renowned institutions around the world. He worked at Kent State University in Ohio, USA from 2010 to 2012. He then joined the Indian Institute of Technology, Kanpur from 2012 to 2014. His international experience extended to Lund University in Sweden in 2015. Dr. Kanavde's research interests are broad yet interconnected. He has extensively studied aerosol microphysics, particularly the formation and growth of atmospheric new particles. His work on aerosol radiation cloud climate interactions has contributed significantly to to understand the role of aerosols in climate change, Dr. Kanavade is a leading expert in satellite remote sensing of trace gases and has advanced knowledge on air pollution. In 2023, Dr. Kanavde's groundbreaking research was honored with the SERP Science and Technology Award for Research, a prestigious recognition for his outstanding contributions to atmospheric science. Dr. Kanavde's research continues to shape the field of atmospheric science. Through his work on aerosol microphysics, air pollution, and satellite remote sensing, he has made invaluable contributions to the understanding of atmospheric processes, with implications for air quality, climate change, and environmental policy. We are really privileged to have him with us today. Over to you, sir. Vijay, sir, over to you.
Yeah, it's for such a nice introduction. Let me share my screen. Do you see my screen?
Yes, sir, it is visible.
Yes, sir, your screen is visible.
Let me bring out the laser pointer. Okay. Yeah. Okay, thank you again, Dr. Kulkarni, for such a nice introduction, and organizers for having me here to talk about atmospheric aerosols. I was thinking to talk about the climate significance of atmospheric aerosol, but then I had been told that the participants are from diverse background, from social sciences to engineering to medical. So I thought it's better to talk about, societal significance rather than just the climatic significance. So my talk is basically on atmospheric aerosols, and they are very tiny particles and with a very large societal significance. Okay. Let me start with a quote, which is given by John Atkin. And let me also say that, I see there are a few experts in the participants or presenter. So you may please excuse me because, of course, you will probably know all the details. So John Atkin, who is a Scottish meteorologist, physicist, and marine engineer, founder of aerosol and cloud physics, built first instrument which actually measures the dust and fog. And what he said was, we have in this fine dust, referring to atmospheric aerosols, a most beautiful illustration of how the little things in the world work great effects by virtue of their numbers. And you can see the examples like sunset and sunrises that we see in the morning and evening is because of the scattering of longer wavelengths by these particles, and we see such a fascinating, beautiful sunset and sunrises. Another example is halo. I think you most of you might have seen it around the moon or sun. It's mainly because of the ice particles that are present in the atmosphere and which scatter the light in different direction. John Atkin is, one of the he has made immense contribution to aerosol science field, and he is one of the first who developed particle counters, which actually measures the number of aerosol particles or dust particles that are present in the atmosphere. Who is the one who basically talked about urban areas which are heavily polluted because there are lots of aerosols in the air and so on. So I will not go into the long list of his contribution to the aerosol science. Let's talk about what are atmospheric aerosols. Atmospheric aerosols are nothing but the solid or liquid tiny particles suspended in the air that you don't usually see it by naked eye. But if you are from rural area or region, you would definitely recollect the figure on the left side where you have light coming into your home, and you can clearly see there are small particles in the air. So you can see only when they are present in very high concentration by naked eye. For example, haze in the morning that you see. So it means there are lots of aerosol particles in the atmosphere. Aerosol particles or atmospheric aerosols play a critical roles in let's say air quality or regional visibility. It also interacts with the radiation strongly, also modifies the cloud properties and therefore the rainfall and therefore the hydrological cycle and in turn climate as well. It also impacts human health. And all these effects are depend on their size, how big and small they are, their number of mass, number of particles or the total mass of aerosol particles in the atmosphere, then their composition, what are they made up of, and their optical properties. I'll come to optical property, what it means basically. So you can see two images below. One is the famous London smog disaster, which happened in 1952, which killed more than 8,000 or 4,000 people, and which was mainly from the industrial pollution by the fossil fuel burning. And the picture on the right is basically the India Gate, Delhi. You can see on the nice, clean day, you can clearly see the India Gate, but on a hazy day or a foggy day or a polluted day, you barely see the India Gate. So the Great London Smog in 1952, you can see in this figure, along x-axis you have a date from 1st to 15th of December, and this smog occurred between 5 and 10 December 1952. It's a long back. And on this axis, you have dates per day, and sulfur dioxide, which is one of the major emitter from the industrial activities or vehicular emission or fossil fuel burning in general. And on the right axis, you have a smoke, which is emitted to the atmosphere. So you can see the number of days, as the sulfur dioxide concentration increases, the number of days increases. It's mainly because of the very high concentration of, particles or the gases in the atmosphere, which mainly affected the elderly and the younger population. And it almost killed 4,000 people over this 5 days duration, and subsequently around 8,000 people died. And subsequently, England had a Clean Air Act in 1956 and 1968, and also the City of London Act in 1954 to curb these kind of smog events or high pollution events. Aerosols are in principle a component of what we perceive as a smog or haze. And WHO, World Health Organization, recommended air quality standards, for a globe, and every country has its own national ambient air quality standard. So as per the WHO recommendation, the healthy air, which is good air, we say when the PM 2.5 or particulate matter less than 2.5 micrometer, or it is put in a general way, aerosol mass is less than or equal to 15 microgram per meter cube. So you can see now this image here, which is from Beijing, China on 12th of July. And the aerosol concentration, mass concentration is about 8 microgram. And as the concentration increases, you can see the visibility decreases significantly. And the picture on the 10th August, it's quite common, especially those who are from Delhi region or North Indian region. This is probably every day's situation in winter time. You have lots of a fog or hazy condition, not just because of the primary emission at the ground, but it's also the meteorology, which makes the condition even worse. So it is important to know what you breathe in, particularly the trace amount, because we know that air constitutes about 78% of nitrogen and 21% of oxygen. And there is 1% which is, trace amount, but that basically includes everything, your, ozone, particulate matters, or other harmful gases. So then the question is, how big are aerosol? Aerosol exists in a wide size range with the 4 or to 5 order of magnitude difference between the smallest and the largest particle. Okay, so if you want to just compare with the thickness of the hair is about 50 to 70 micrometer, and the smallest particle you could have is 1 nanometer, which is 10 to the power minus 9 meter or 10 to the power minus 6 micrometer. Okay, so it's basically 1 by 200 times of the diameter of human hair. So basically you can't see it by naked eye unless it is present in the very high concentration. And you can see the images on the left side, right side, of a fly ash or organic particles or mineral, which comes from the dust. The soot that you burn, wood or agriculture burning. So the soot comes from mainly from there. Then what are the different sources of atmospheric aerosols? Of course, there are two types of sources. One is natural sources. Those are the aerosol that comes from the natural activities, like volcanoes, for example. You have a lot of fly ash and dust. Then sea salt is mainly because of the bursting of bubbles. It injects the aerosol particles into the air, what we call as a sea salt, and you can actually smell that when you go to the beach. Then dust, which could be the dust storm or wind-blown dust, or it could be from construction, or the simple example is if you see the vehicle running on unpaved road, you can see a lot of dust is suspended. But after 10 seconds, the dust is gone because most of the dust particles are much bigger, so they settle, and some of them remain in the air suspended. The anthropogenic activities include the fossil fuel or biomass burning, mainly industrial activities, vehicular emission, biomass burning, or the solid waste burning. In addition to the primary sources, so these are the mostly primary sources where you have a direct injection of aerosol to the atmosphere. We have a major fraction of aerosol that comes from the secondary production, where you have some kind of physiochemical transformation, or different gases react with each other in presence of the sunlight, and they form new particles in the atmosphere. Okay, so I'll talk about that also in the subsequent slides. Now, then next question is, how long do aerosols remain in the atmosphere? So once they are emitted to the atmosphere, how long do they remain in the atmosphere? So their lifetime varies based on where they are emitted, first of all. Secondly, with the size. So along x-axis here, you can see the size. Along y-axis here, it's basically the lifetime. So you can see the smaller the particle or the bigger the particle, they have much shorter lifetime because the bigger particle will settle down, as I just said. And the smaller particle, because it is too small, it will be highly mobile. So it's most likely, it will be scavenged by some other big particle. But the particles which are between, let's say, around 100 nanometer or 200 nanometer, they have a long lifetime, maybe a week or so. And that's where the most of the aerosol number concentration dominate. Most of the anthropogenic activities like vehicular emission or biomass burning or forest fires, most of the aerosol that are emitted, which are around 100 or 200 nanometer and so on. But on an average, aerosols have a lifetime about 7 days in the atmosphere or in the troposphere. Okay, the next question is, what are aerosol made up of? Okay, then of course we have two categories, primary and secondary. So primary particles which contain basically carbonaceous matter. So you have organic carbon, elemental carbon, or you have a fly ash, dust. So if it is dust, then you have several different minerals, so calcium, magnesium, and potassium. Then there are also some of the gases, as I mentioned, like sulfur dioxide, which can be oxidized in presence of the sunlight, which form the sulfuric acid, and which can also form, aerosols by reacting with, let's say, other basic compound like ammonia or amines. So we have ammonium sulfate. Then we also have a NOx emissions, which can also form particles like a nitrate particles. Then we have lots of volatile organic compounds emitted from not only from anthropogenic activities, but also from trees, the plants, what we call as a biogenic volatile organic compounds. They also undergo photochemistry in the atmosphere, and they also form what is called the secondary organic compound. So basically, I just listed down here a few compounds, I must say, because there are several different compounds that constitute the aerosols. So black carbon, organic matter, ammonia, sodium, calcium, magnesium, potassium, and so on. Okay. Okay. Now the picture on the left is basically just showing you the composition pie chart, and you can see that, and it's for the Beijing, basically China. You can see that in here, organic matter dominates most, followed by sulfate, and then nitrate, and then ammonium. And then, of course, you have some other trace amount of chloride and then some major trace material, and there is some amount which is unidentified. Then if we look at the different sources that they come from, you can see that the coal burning or the secondary contribution, like as I just said, through some kind of physiochemical transformation, these are the three things which dominate the most. So secondary inorganic rich or secondary organic rich. Organic mainly from the volatile organic compounds, inorganic mainly from the sulfate or nitrate and so on. And of course, there will be some biomass burning, and then you have some dust related. Now, if you come to India, this is one of the figure which again shows similar kind of pie chart for aerosol composition. We have organics, ammonium, nitrate, sulfate, and chloride. And again, you see similar kind of behavior here, with the organics being the dominant contributor, followed by you have sulfate and nitrate. But there are places like in Delhi, for example, if you see, you have lots of chloride here, which I think mainly comes from the industry. And there are also places like Kanpur here, you have a lot of chloride, and then Chennai also you have some chloride, but there are a few places where you don't have much chloride. So in a way, you have a strong spatial variability in aerosol composition. So they do not have the similar kind of composition across, let's say, whole India, or just put it on a global scale also. It's a very different. Okay, now how do we classify aerosols? Aerosols can be classified by various ways. One is, simple way is tropospheric and stratospheric. If you do not know what is tropospheric and stratospheric, troposphere is the layer which is, close to the Earth's surface, from surface to about, let's say, 15 or 20 kilometer, and the stratosphere is just above it, from up to 50 kilometer. So why do we classify this way? Because they have different lifetimes, they have different composition in these two different layers of the atmosphere. Then we also classify based on their source, natural and anthropogeneous, because again, they have different properties. We also classify based on geographical location, marine location, because we have mostly sea salt aerosol from there. Continental is mixture of almost everything. Rural region, industrial region, polar region, or desert region is mostly the dust aerosols. We also classify based on the chemical composition, soot, which mainly comes from the biomass burning, or fossil fuel burning, sulfate, organics, dust, sea salt. We also classify based on the mechanism, as I said, primary, which are directly emitted to the atmosphere, and there is also other mechanism by which aerosols are either transformed or formed newly in the atmosphere, what we call as a secondary mechanism. And then lastly, I think we classify based on the size, because each size has different in impact, in terms of air quality or climate or human health, for example. So ultrafine particles, which is, which has probably more impact on the human health, because these are the particles we could, inhale, and they can reach up to the lungs. Fine mode, and then the coarse mode, which are really big particles, which can scatter the light efficiently. So it's a good climate potent aerosol. And then finally, characteristic property, because as I said, the aerosol is made up of, of different compounds, and depending upon the compound, it has either the absorption property or the scattering property. Okay, this is the best example. The two types of aerosol particles, those absorb sunlight, so soot and BC. So they will warm the air if they absorb our atmosphere, and the particle, those reflect or scatter the sunlight, like sulfate, dust, and so on. They will scatter the sunlight, so it will cool down. So this picture, basically what you see here is, the soot or BC, which comes from the wildfire smoke or agriculture, which is shown in the orange color. And then you can see the dust particles from the Sahara or the Gobi Desert or the Thar Desert, which is shown in the purple color. There are sea salt aerosols locked in the typhoons, over the sea. You can see the sea salt aerosols, or in hurricane, and so on. So depending upon the type of particle, you have a different aerosol property. So why aerosols are referred to as a complex driver of climate? It is indeed a complex driver of climate because there are several uncertainties associated with the aerosols when it comes to the its radiative forcing. It's mainly because of its different diverse properties. One is physical, which basically means the mass, number, size, and morphology. Because not all the particles are spherical. For example, dust particles, they are not really spherical. But if you talk about the organic particle or the sulfate particle, they are, quite spherical. The size, as I told, the size is very wide size range, from 1 nanometer to up to, tens of micrometers. So there is a 4 or 5 orders of magnitude difference between the smallest and largest. And mass and number, because it basically dictates, the its impact on the climate or the air quality and so on. Then you have dynamical properties, which mainly basically constitute the secondary formation of aerosols, where you have a formation of aerosol, what we call as a nucleation. I will talk about that. The coagulation, where the aerosols are removed from the atmosphere. The condensation, where the vapor diffuses onto the aerosol, which grows the aerosols in the atmosphere, and so on. The chemical properties composition is hygrophobicity. This is one of the important factor, from the point of view of cloud formation and the rainfall, volatility, mixing state, and so on. Let's not get into detail. And then the optical properties. So all these properties have, very large variability depending upon the type of aerosols and the location and the source and so on. Now, once they are emitted to the atmosphere, its aerosol evolution depends on many factors. Once the kind of aerosol that is emitted to the atmosphere, its size, its composition, and you have what is called the long range transport, because of course there's a wind which can transport aerosol from one location to other location. So even if you have a burning at one particular location, so the wind can transport those aerosol to the downwind regions. What happens, for example, in northern India during the winter time, mostly because you have wind from northeast. So whatever you burn in, let's say, on the northwestern parts, it's basically impacted in the northeast part. Then you have in-cloud aerosol production, or clouds, clear air aerosol production, which is the second aerosol production. And then those are the very big particles which can dry or wet deposited to the ground. So dry because of their weight, or because of their size, and weight when there is a rain. So you can notice after the rain, it becomes very clear and visibility is significantly improves. There are different platforms that you can use to measure atmospheric aerosols, starting from ground-based measurements, where you can have in-house instruments or some kind of, analysis, or you can collect aerosols on some kind of filter papers and, go to the laboratory and do some kind of chemical analysis. You could have LIDAR-based measurements from the ground. Then there are also unmanned aerial vehicles like, drones. We could also do measurements with the vehicle-based instruments. We also do measurements using the tower-based instruments, just to see the variability, of aerosol between the surface and the higher Earth. We also have measurements using the tethered balloon, where these balloons can go up to a certain height, 1 or 2 kilometer, and we can have measurements at that particular height above the surface. And of course, airborne measurements using the aircraft and the satellite measurements. So they are measured using very different platforms. In addition to modeling, of course, we have different models that basically use to simulate aerosols in the atmosphere. And the picture on the left, I just thought I should show you how does aerosol concentration vary with the height. So this is the surface, 0 kilometer at the surface, and you can see you have highest concentration at the surface. As you go higher up in the atmosphere, the aerosol concentration decreases up to certain height, 10 or 15 kilometer, and then it increases again, peaking at around 20 or 25 kilometer in the atmosphere, which is basically stratosphere. And these are mainly the sulfate aerosol, what we also call a Junge layer. And Junge is the name of the scientist. Okay, now why is aerosol science so important and it's also so critical? Now, I'm sure that everybody knows about the global warming and the culprit of global warming, greenhouse gases, mainly carbon dioxide and methane. And if you talk about the quantification of greenhouse gases, in a way it's certain, precise, and we know very well that uh, it is the main reason for the global warming. So you can see this picture, very famous picture of carbon dioxide time series from 1952 till present, and you can see that how nicely carbon dioxide concentration increasing at Mauna Loa Observatory in Hawaii. Now, the one other reason why it's certain and precise is because carbon dioxide has a very long lifetime. It's very well mixed in the atmosphere. So even the point observation, which we have from Mauna Loa in Hawaii Island, is representative of a global mean concentration, which is not the case for aerosol, for example. And there is, of course, linear relationship with temperature, which is also, again, not the case for aerosol. There is no linear relationship. Everything is very non-linear, dynamic processes, whether you talk about air quality or the cloud formation or the rainfall or the climate impacts or even the human health impacts. And for greenhouse gases, of course, we know the sources very well, and they have been characterized very well. So, kind of a very precise quantification for, to understand their climate impact. But when it comes to the aerosols, it's quite uncertain. One is because aerosols are highly variable in size, composition, and lifetime. This is what I was mentioning earlier also. And there is a strong spatial temporal heterogeneity in aerosols, makes it even difficult or hard to quantify them and to accurately measure the climatic effect, whether it's a cooling or warming effect, depending on the again composition in the atmosphere. Okay, now if you see, this is the global aerosol map. The color basically shows the aerosol concentration, particles per centimeter cube. Lowest is 10 particles per centimeter cube. Highest is about 10,000 particles per centimeter cube. And you can see there is a large variability. You have higher concentration over US, Europe, India, China. You have much lower concentration over the ocean in general. You do see some high concentration or, medium high concentration over the oceans. It could be transported. You can see the outflow also from the continent onto the sea. But if you compare these concentration, from 10 to about 10,000 particles with the global pre-human background aerosol concentration, which is about only 300 to 500 particles per centimeter cube. So most of the aerosol concentration, if you see, is over the continent, which is, where you have a strong emission or higher emission rates, Europe or India or China or US and so on. Now, is the aerosol concentration increasing? Okay, this is very crowded figure. Basically, what they have done here, they have looked at the temporal evolution of aerosol concentration based on several different data sets. So I'm not going to go into detail of each of these data sets, but some of them are a satellite instrument, and one of them is basically the model. And they have looked at all these regions where the aerosol concentration is increasing or not. Let's look at maybe Eastern US, for example. And they have looked at it seasonally, December, January, winter. This is fall or post-monsoon in our case, or summer or monsoon, and then spring or pre-monsoon in our case. And let's look at the annual. So for Eastern US, you can see from 1980 till 2000, I think, 10, the aerosol concentrations are decreasing in recent times. If you come to the South Asia, the aerosol concentration are increasing. Of course, this includes India, and the Northeast Asia, which is basically China, which is here. This is Japan. You can see the aerosol concentration are decreasing. So only the Southeast Asia, these are the regions where aerosol concentration are increasing in recent years, but most of the other regions, aerosol concentration have started declining in last a decade or so. Okay, now I'll talk about our one of the key finding where we showed that there is a recent increase in winter hazy days over central India and the Arabian Sea. And what basically we said that the number of days with high aerosol loading, what we call as a hazy days during the winter season, is increasing at much faster rate over central India than over the Indo-Gangetic Plain. And this research was also highlighted in some of the media, newspaper, the Hindu, in New Indian Express, and so on. There have been several studies over last almost 3 decades over India, which basically reported that there is a increasing trend in aerosol loading over the Indo-Gangetic Plain. Uh, more trend over the Indo-Gangetic Plain than compared to the other regions. Well, our question was, is the increasing trend in aerosol loading is same all over the India in recent years? So this was our question. So for that, what we did is we used the data, 15 years of data from 2003 to 2017 from satellite over the India for the dry winter season, which is November, December, January. And then we divided this particular time period into two different time periods, 2003, 2007, which is the past years, and 2013, 2017, which is the recent years. And what you see here is the difference between the past and the recent. And basically the positive difference indicate that there is more aerosol concentration in recent years than the past years. And that's what we see that, almost over entire India, there is a very high positive difference in aerosol optical depth or aerosol loading, in simple words. But there is much higher over the central India than over the Indo-Gangetic Plain, which is, pretty much white. So it's around like, 10 to between -10 and +10%. But if you see over the central India and the part of Arabian Sea, the percentage change in aerosol loading over this region is about 80% or so. Then what we did was we calculated the number of days with the low aerosol loading, then medium aerosol loading, and the high aerosol loading. And this is what is being plotted here. So this is the trend in the number of days, or trend in the number of days with aerosol, low aerosol loading. This is the trend in number of days with medium aerosol loading, and this is trend in number of days with high aerosol loading. What you see here, basically, there is a decreasing trend in number of days with low aerosol loading over India, except maybe here, I don't know why. But if you look at the trend in number of days with high aerosol loading in India, it's increasing significantly, about 3 days per year. And what was surprising for us is, central India, where you have very high number of, 3 or 4 days per year, whereas Indo-Gangetic Plain, which is, most populated, polluted region, where the aerosol concentration are increasing, but not as fast as that are increasing over the central India. Okay, so in addition to the, so basically so far I have not really, categorize into whether it's a primary or secondary. Of course, based on the satellite measurements, I would know how much the contribution of primary and secondary. So that's basically, important aspect, which is again poorly quantified, especially in Indian context. Okay, how much is the airborne secondary production of aerosol that is there in the atmosphere, if let's say for India. And I'll just try to explain why it is, important first before I talk about that. So if you have a direct emission, let's say, you burn a wood, you can see the soot particles coming out. So that is the direct emission of aerosol to the atmosphere. Okay. So it is straightforward to mitigate. You can just cut down the source. So you can reduce the aerosol concentration. And the climatic effects are also quantified adequately because precisely the composition of those, particles. Let's say you burn petrol. So you know exactly the composition of those aerosols and the size of you burn wood. So it's a mostly soot, BC, and its property. So as far as direct emission concern, it is possible to mitigate, and the climate effects are also quantified adequately. But when it comes to the airborne secondary production, it's basically intricately mixed with the primary emission, first of all, And the secondary production is not a linear process, it's a non-linear process, and it's very dynamic. And this is one of the processes which dominate aerosol number most in the atmosphere than the primary emission. And it's very difficult to separate out, how much is primary and how much is secondary. Okay, because it's a very complex coupling between the primary and the secondary. So what we have basically, you have different kinds of, gases that emitted, because whatever you burn, let's say you're burning wood, you can see the soot coming out of it, but you don't see the gases that coming out of it. Or you burn petrol, you can see the, you can see the vehicle exhaust, you can see a lot of smoke coming out of it. But what about the gases? Do you see it? No. So there are, the precursor gases that also comes out from each of these anthropogenic sources or and the natural sources. They can undergo chemical reaction in presence or absence of sun at times, and they can form small molecular clusters which can grow in the atmosphere in size by vapor deposition onto this cluster, and then eventually can reach much bigger sizes where they can have climatic effects and so on. So what it is basically nucleation, which refers as hello. Yeah, so nucleation, which basically refers as the formation of a stable condensed phase by aggregation of same or different molecules. So here, for example, you see you have biogenic vapors or sulfuric acid. They can nucleate or aggregate together to form a small clusters, and these clusters grow in the atmosphere by additional vapor deposition, what we call as a condensation. And once they become stable in the atmosphere, they can they can grow much uh, bigger in size in the atmosphere. There are two types of nucleation. One is homogeneous nucleation, where only the gaseous molecules aggregate and form molecular clusters, and the other is heterogeneous nucleation, where the foreign particle or the aerosol particle that are present in the atmosphere is grown bigger by the condensation of additional vapor. Now, the question again, what compound lead to secondary aerosol formation? Okay, so for that we need to understand what is the saturation vapor pressure. Saturation vapor pressure means a substance is a very volatile, and if that is the case, the molecules will easily escape the surface from liquid surface, and they will not stick back. So in order for nucleation to occur, you need a vapor which has very low saturation vapor pressure, so they are non-volatile and they stick together. So sulfuric acid is one, which is basically we referred as a main vapor for aerosol nucleation or particle formation. Because there are several other compounds, especially from the biogenic or anthropogenic volatile organic compounds like highly oxygenated molecules, organic molecules. Now, if you see the water, which has very high saturation vapor pressure, and this is the reason why water molecules cannot nucleate and form cloud droplets. Okay, in order to form a cloud droplets, you need aerosol. So I'll come to that also in the subsequent slide. And then once these clusters, which are, as I said, 1 nanometer or one to 2 nanometer, they form in the atmosphere, there are two possibilities. One is they grow in size by vapor deposition of, some organic matter or some condensable vapors, and they grow, much bigger size, greater than 1 micrometer or 50 or 100 nanometer, where they can have, air quality or climate effects and so on. Or they can also be scavenged by the pre-existing aerosol particles. So what we call as a coagulation loss. Okay. So the fate of newly formed particles is decided by competition between these two processes. Now, if you look at the Indian context, as I said, it's very not really vaguely studied, but I would say we do not have really a good understanding of secondary aerosol formation over India. And this is the map of Modi's retrieved aerosol concentration (AOD). You can see your Indo-Gangetic plain, you have high AOD, and then rest of the India, you have much lower AOD concentration. And all these different sites are the location where the secondary aerosol formation has been studied over India. And you can see that it has not been studied across India very well, mostly from urban regions like Pune, Hyderabad, Kanpur, Delhi, and so on. And there are a few studies from Himalayan region as well. Now, there are several knowledge gaps, when it comes to the secondary aerosol formation in India. One is, what is the chemistry driving new particle formation or secondary aerosol formation in different environments? It's still mysterious. We don't know which are the different species that, that goes into the secondary aerosol formation in India, because we don't have measurement. Secondly, the fraction of these particles that grow into, climate relevant aerosols. Okay. Then what is the relative importance of traffic and biomass burning emissions for second aerosol formation? It's still an open question, because it's something that is not being studied, with let's say state of art instrumentation. Then relative roles of volatile organic compounds to the second aerosol formation, and so on. Now, does second aerosol formation significantly contribute to total aerosol? So this is a study from China, where they have shown that about more than 80% of 80% comes from the secondary aerosol formation, and then only 20% is from the primary. And they basically looked at one particular mode, which is accumulation mode, which is from 100 nanometer to about a micrometer. But that is still very significant, and this is the reason why we should, look at the second aerosol formation and their mechanisms, and so on. So the direct emission, as I said, it's easy to mitigate, because it's straightforward to mitigate. You can cut down the primary emission, but reducing primary emissions of secondary aerosol precursor is also important. It's not just the aerosol particle that emitted, but the aerosol precursors that are emitted along with those particles is also important to reduce, in order to reduce total aerosol mass from the atmosphere. Okay, so I'll talk about some of the implications of aerosol precursors. One of the example is, everybody knows acid rain, which was discovered back in 1970s. Sulfur dioxide, which mainly comes from the industrial pollution or the traffic emissions, and also the NOx, also which comes from the industrial and traffic pollution. Sulfur dioxide can oxidize to form a sulfuric acid, and the NOx can oxidize to form a nitric acid, which forms aqueous solution. So when these gases are dissolved in the cloud droplet, they can form weak solutions of sulfuric acid and nitric acid. That's how you can have acid rain. Of course, you will not have always. You will probably have very next to the industrial region, where you have lots of emission of SO2 or NOx and so on. So this is the map below shows the wet sulfate deposition. It's nothing but the amount of sulfate that was dissolved in the rainwater. So basically they did the rainwater collection, and the laboratory they found out how much is the sulfate deposited, or how much is the sulfate that is dissolved into the water that they collected from the rain. And for US, you can see that this is from 1989 to 1991. You have very high concentration of wet sulfate deposition, and in 1997-99 it has significantly reduced. In fact, in 1980s or so, or 84, they have I don't remember exactly the name, but they have some kind of rain experiment where they were mainly looking at the rainwater. They were collecting rainwater samples across US, and just trying to figure out what are the different compounds that dissolved into the rainwater. Of course, we are also doing the same thing over India. But this is the picture from 1990 for India. You can see you have some wet deposition over India and China, and this is not up to date, I must say. This was projected maybe about 10 years back, that we will have very high wet sulfate deposition India and China, and I don't think that is wrong. Maybe not quantitatively correct, but qualitatively we can say that India and China has more wet sulfate deposition in recent years. This is the case for Germany, for example. You can see from 1982 to 1995, sulfate is decreasing over the time. pH is increasing, so it's getting more and more basic from 4.2, which is really acidic, and now in 1995 it becomes 4.8 or 5. And I'll just show you one image, which is photographed in 1908, this one, and this is 1969. So the photo is taken about 60 years, apart, and you can see the severe deterioration, probably due to, acid rain. It's most likely due to the acid rain. Okay, now we'll talk about the trends in particulate matter or aerosol concentrations over some of the selected regions. So this map here shows basically trends in particulate matter to less than 2.5 micrometer. And the negative color, the blue color means the negative trend. The red colors mean the positive trend. So you can see over India and part of China, you have an increasing trend in particulate matter pollution. Whereas in over Europe, USA, you have a decreasing trend. So if you look at more closely, Eastern US, from 1998 till 2018, you have a nice decreasing trend in particulate matter pollution, same as for the Europe. But if you come to East Asia, you have kind of increasing trend initially, and then from I think 2011 or 12, they have a decreasing trend. That's what you see here. There is a part where you have a strong decreasing trend, and there is a part where you have increasing trend. So altogether, it looks like something like this. And if you come to the India, you can see there is an increasing trend, and we also have, for some regions there is a decreasing trend. Especially, I think I'm not too sure about the particle pollution, but if you toward, let's say, SO2 emissions. So Delhi, for example, or one other, Ahmedabad, I think it has a decreasing trends in SO2 that we can see from even satellite measurements. Okay, so this figure again shows the same thing, PM concentration trends. So positive means increasing trend, negative means decreasing trend. And you can see the China, you have a slightly decreasing trend, but there is a more of positive trend. India, it's mostly the positive trend in the particulate matter pollution. Southeast Asia, you have again increasing trend. Northern America, mostly decreasing. Western Europe, decreasing trend. The tropical Southern America is also, you have a decreasing trend. And if you look at, rest of the world, it's basically, you have a, seesaw. You have decreasing as well as increasing trend. Okay, now, I mentioned that it's very critical, to quantify aerosols climatic impacts is mainly because of, strong spatial temporal heterogeneity. So it's not just the spatial, but it's also temporal. What I have plotted here is the pie chart of aerosol composition for different seasons. You can see winter, pre-monsoon, monsoon, and post-monsoon for different regions, Delhi, Kanpur, Bhubaneswar, and so on. Now, if you just focus on Delhi, what you see here is, the composition of aerosol throughout the year is mostly dominated by organic matter, and then followed by sulfate, and then ammonium, and the nitrate, and the chloride. But you see there is still variability in organic matter on even sulfate, because sulfate is more in the monsoon time than the other seasons, and so on. And you can see the similar patterns for other regions like Bhubaneswar or Chennai or Mahabaleshwar. There is a strong spatial temporal heterogeneity in aerosol composition as well as their sources. One source, which is basically traffic. I mean, there are two dominant sources, I would say, in my opinion, is mainly traffic and industrial sources. So this is pretty old study, probably 2010, I believe. Where they looked at the traffic contribution to PM 2.5, particulate matter less than 2.5 micrometer, for different types of vehicles. So you can see trucks, which dominates about 40%, followed by two-wheelers, two-stroke, and so on. Now we have almost four-stroke and all these things. Okay, I'm sure most of you have come across this. World wonder Taj Mahal is turning brown due to air pollution. So this is the study which was carried out by Georgia Institute of Technology, the University of Wisconsin, the Indian Institute of Technology, Kanpur, and the Archaeological Survey of India. And they performed one collaborative study where they showed that pollutants are, is the major cause of discoloring the Taj Mahal. Okay, so this is basically the image of the Taj Mahal marble, and you can see this is the marble surface and these are the particles, and they concluded that the light absorbing dust particles and the carbonaceous particles are responsible for the surface discoloration of the Taj Mahal. And more recently, I think municipal solid waste and cow dung cake burning also have been banned, around Taj Mahal area. Okay, now let's briefly talk about aerosols impact on human health. So if you notice, I have pictures of different age groups, starting from younger to elder. So it's very common that, aerosol doesn't see what age you are. Basically, it impacts everyone. And I must also say that it's not that, you see the its impact or effect on your health immediately. Mostly it's silent killer, that's what we call it. But you do have a, immediate effects like, eye or nose or throat irritation if you are exposed to very high concentration. Or, those people who have asthma, they will have problems of breathing when, it's in walking in, let's say, hazy condition or foggy condition. So it can lead to the improper development of children's lungs, trigger asthma attacks, coughing, difficulty breathing, eye, nose, throat irritation, or even heart diseases if one exposed very long, over very long time, for very high concentration of aerosols, abnormal heart rhythms. And one of the best example I gave in the very first or second slide, when I talked about the London smog, 1952, which was like immediate effect of aerosols, for example, from the sulfate aerosols, which or maybe or the coal burning aerosols. Now, this graph basically shows the deposition fraction on the y-axis from 0 to 1 in human respiratory tract, and x-axis is the particle diameter. So this is the smallest particle diameter, which is about 0.01 micrometer, that is about 10 nanometer. This is 100 nanometer, and this is 1 micrometer here. And you can see for the nasal, so most of the bigger particles are blocked in your nasal thing, and then most of the smaller particles can reach to your lungs deep down. And if you look at the deposition fraction, about 60% of the particle can reach to your pulmonary tract or even the lungs. So they can really reach down deep down into the lungs and then impact the smaller the ultrafine particles can affect your tissues and so on. And it's not just the aerosol particles, because basically when you inhale all gases as well. So for example, carbon monoxide is another gas that comes from the biomass burning or traffic emissions, which can also impact your tissues and even blood streams and so on, if one exposed to very high concentration. Yes. Okay. When, as I said that air pollution is a silent killer, and this map basically shows the distribution of premature deaths that is attributable to the household solid fuel use. Now, if you see, most of the developed countries, it has very less population per 1,000 people, which is attributable to the household. But if you come to India and Africa, you have about 4 people, 1 person for every 4,000 population, which is dying because of the household solid fuel use. And when it comes to the share of deaths globally, of course, India, China, and some countries of South Africa contributes, about 10 to 12% of deaths globally due to air pollutions. Okay, now I am into the last part of my talk, where I'll mostly focus on the aerosol's impact on the climate. But before I do that, I just want to introduce what is IPCC, but I believe that you already know because I think other speakers might have talked about already Intergovernmental Panel for Climate Change, its role and key principles. So IPCC doesn't do its own research, but it triggers research. And the main role is understanding the scientific basis of risks of human-induced climate change, its potential impacts, and the option for adaptation and mitigation. So IPCC reports are neutral with respect to policy because each country can have their own policy. So we had first IPCC uh, report back in 1990, and the IPCC was jointly established by World Meteorological Organization and United Nations in 1998. Subsequently, we had first, second, third, fourth, fifth, and now we have the sixth assessment report of IPCC. And these are some of the key points of recent IPCC report, where the main highlight was limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. Human influence on the climate change or climate system is clear. Warming in the climate system is inevitable. Okay, then what is radiative forcing? Okay, let me talk about radiation budget. So this is the amount of solar radiation that we receive every meter square, 342 watts per meter square. And let's say we assume it as 100%. So out of that, whatever the energy that we receive, 51% is absorbed by the land and ocean, and remaining, is absorbed by the atmosphere, and some is scattered away, what we call as albedo. So let's not go into it. But if you see the amount of energy that is being absorbed by the land and ocean, the same amount of energy is re-radiated by the land. So you can see the 23% by latent heat, 7% is a sensible heat, and 21% is a long wave radiation. So if you sum up, it will come as a 51%. So there is a balance between the absorbed and re-radiated. And if you see the total income is 100%, so total outgoing should be also 100%. So you have a 64% emitted by the clouds, water vapor, CO2. Then you have 6% emitted by to the space, and then you have about 30% reflected from clouds and water. And if you put this together, you have 100%. So there is a balance between incoming and outgoing. So in practical, if we have this balance, there should not be global warming or cooling. But of course, there are factors like greenhouse gases, aerosols, or changes in solar energy has led to imbalance referred to as a radiative forcing. So difference between the energy that entering and leaving the Earth's atmosphere. So if it is a positive, it means it's a warming the atmosphere or warming the planet, and if it is negative, it means the cooling the atmosphere. Now, our interest here is mainly aerosol, so we're not going to talk about other climate drivers, and these are the aerosol processes where you have different kinds of aerosols, which has a direct effect. I will talk about that, what it is. And there is also what is called cloud adjustment due to aerosol, what we call as the indirect effect. And this is not the up-to-date figure. This is from IPCC 2014. I intentionally used this because I wanted to show this particular column here, which is level of confidence. And you can see for all other climate drivers, it's either very high, or medium, and so on. But when it comes to the aerosol, cloud adjustment due to the aerosol, the level of confidence is low. It means there are a lot of uncertainties understanding the aerosol and cloud interaction and so on. So the question is, how do aerosol influence climate? One is by interaction with the radiation. Other is by affecting cloud properties and thereby hydrological cycle. Okay, now interaction with the aerosols. So there are two possibilities. Aerosols scatter the sunlight. So that is basically direct effect that will lead to the cooling, or they can absorb the light, which will warm the atmosphere and again cool the surface, but over the very large region, it will have a warming effect. Okay, but over the very small region, it may have a cooling at the surface and warming in the atmosphere. But if you look at the large scale, there is a net warming of the surface of the atmosphere. Okay. Now, second is affecting the cloud properties and thereby Harold cycle. Now, in this picture, what you see is there is a liquid water, and this is the rate of condensation, and this is the rate of evaporation. So when the rate of evaporation is less than rate of condensation, then we can say that air is super saturated with respect to liquid water. So there is a, the vapor, if you calculate the vapor pressure of water vapor, saturation vapor pressure would be much higher. So this is very good condition for a dew formation that you see usually, especially during the winter time, temperature much cooler. So water vapor can condense onto the, surfaces. For example, on the grass or your, trees or your vehicles, you can see there are, water droplets. Now, what about in the atmosphere? In the atmosphere, this surface is provided by the aerosol, what we call as a cloud condensation nuclei or aerosol. So not all aerosols act as a cloud condensation nuclei. Only a fraction of aerosols act as a cloud condensation nuclei. Why is it so? Because not all the aerosols are water absorbing or hygroscopic. There are some aerosols which are water hydrophobic, which repel water, which does not attract the water. Okay, so those are not really good cloud condition nuclei. So what we need is hygroscopic nuclei. Now, for example, sulfate or dust or maybe some organic fraction. They are, hygroscopic particles. So they can act as a cloud condition nuclei. But some of the aerosols like oil or gasoline, they are definitely not good cloud condition nuclei, and they will resist the condensation and therefore the cloud droplet formation. So in short, if there is no aerosol, there is no cloud, there is no rainfall, and there is no water from the rain. So we need aerosols in order for cloud to form and therefore the rain. Again, it's not that as simple because it depends again on the size of the aerosol and the number of aerosol particles. So for example, I have two pictures here, one of clouds, one cloud with a few droplets, much bigger droplets, and one cloud which is more number of droplets and much smaller droplets. Okay, so these could be called as a clean clouds. These could be called as a polluted clouds. So if you say the clean clouds, they have fewer droplets, so there are more chances of rain from these clouds because the droplets will be much bigger and they will of course fall on the surface as the raindrops. But if you have polluted clouds where there is a deficit of moisture because there are too many small droplets and they are not allowing the growth of these droplets in order for a rain to form. So this will in a way delay the rain process or suppress the precipitation, or you may have only drizzle and so on, and therefore you have very high albedo. So this way you will have more cooling at the surface. Okay, so I'll just quickly talk about 1 hour study where we showed aerosol induced intensification of cooling effect of clouds, or in other words, aerosol induced cloud invigoration, which is basically the dominant process over Indian summer monsoon, which enhances surface accumulated rainfall and the cloud cooling effect. So what we found that there is a positive association between aerosol loading and cloud, which is what expected, and therefore also the aerosol and the rainfall. Okay. So, but as I said here, if you have a cloud over continental region with very large number of small cloud droplet, which will delay the rainfall in a way or suppress the rainfall. But if you have a cloud invigoration with there is ample amount of updraft within the cloud, these droplets can be taken above the freezing level in the within the cloud, and they can grow there more efficiently and then form probably the ice particles and so on. And as a result, you could have a heavier or widespread rainfall. That's what we call as a cloud invigoration. Okay, aerosol induced cloud invigoration. And this is how it can be explained. So this is the natural pristine case. So I will not talk about that. But if this is the polluted case, where you have very high concentration of aerosol at the surface, and you can see the cloud with the smaller droplets, and there is an updraft. Okay, And then even just before the dissipation stage, you have very heavy rainfall because of the tall cloud, which is developed due to the high aerosol concentration, which induce the cloud. Okay, now when I say this, so I don't mean to say that, if you high aerosol means you will have higher rainfall. No, it's not the case. Okay, it's not that simple. There's no linear relationship, as I said. So high aerosol loading will not always produce heavy rainfall because the dynamics and moisture, the atmosphere dynamics, the wind and cloud structure, and the amount of moisture that is present in the atmosphere dictate the amount of rainfall that falls on the surface. But of course, aerosol, you need aerosols also in order to form a cloud droplet. So now here is this is the image I have for you. If I say quickly, find out who is the most talented tennis player. Now I know that there are lots of players which are playing. Now if I really want to understand, it's kind of very puzzling. So if I really have to see two players playing together, observe them for some time and then see how they are playing, then probably I will be able to slowly figure out, okay, who is playing how and so on. Aerosol, cloud and radiation is something like that. It's puzzle. Aerosol impact cloud, cloud impacts rainfall, rainfall also impact cloud, clouds also impact rainfall. Aerosol cloud interaction impacts clouds, rainfall, and so on. I mean, it's a puzzle which involves many physical, dynamical, and even chemical. When I say chemical, I'm mainly referring to the composition of aerosol. And isolating effects of one from other is very difficult, and that's the reason why aerosol cloud interaction or adjustment in cloud by aerosols is one of the least understood process in the climate system. Okay, I think I'll have another probably 5 to 10 minutes. I hope I'm not exceeding the time. I'll just give a couple of examples and then I'll stop. So aerosol-induced haze formations. I think this is a very common image that you see, Taj Mahal, and then you have a haze over India and then the fog. So when you have very large amount of aerosols present in the atmosphere with, at very low relative humidity, you could have what we call as a dry haze, and at high humidity conditions, this can result in the formation of humid haze or small cloud droplets even. So that's why we have the fog and so on. And when there is a fog, of course, the visibility is reduced to less than 10%. Cold wave in Delhi, flights, trains delayed due to fog. This is common. Every winter we have this kind of situation. Now the question is, what are the solution? Now the first and foremost is reduce direct emissions of both aerosols and precursor gases. Okay, so that's what I said, mitigating. It's very straightforward, but is it really possible on grounds? Probably not. Then again, we cannot change the favorable meteorological condition. So we need some long-lasting technological innovation to curb the formation or dissipation. So either you have to curb the formation or you have to increase the dissipation of fog in order to reduce the fog formation or remove. And there was also, one of the severe air pollution episode, what we call as a smog also in November 2016 in Delhi. And, most of the studies actually claim that is mainly because of, there was a lot of biomass burning over the Haryana and agriculture, and basically that impacted or that caused the severe air pollution episode in Delhi. But we showed clearly in our paper that is not the main cause. Of course, it is one of the cause because, it's not just that you have emission in Haryana and Punjab, but you do have emission in Delhi as well, traffic emission and so on. It's main reason what we showed in the paper was the meteorological condition, because we had a very high moisture present in the atmosphere, very high loading, very calm conditions. So you're kind of very stable atmosphere, which lead to accumulation of aerosols where they have emitted. Okay. And this is the last slide or second last slide. Is air pollution is the 21st century really only a urban problem? No, it's not an urban problem. It's actually, it's a rural problem as well. Okay, this is one of the study by Ravi Shankara, which I think published in PANAS back in 2020, and they showed that we have much higher or maybe equivalent concentration of pollution in non-urban areas as well. So if you can see North India or IGP, and these blue ones are green ones are for urban and the orange ones for non-urban, you can see you have more or less same concentration. And what they have done is they have calculated the annual mortality for urban and non-urban. What is surprising is that you have more annual mortality for non-urban with a very large variability than the urban regions. So that was their study. And this is last night. I mean, of course, there are several efforts which have been taken to curb the air pollution, but I'm not going to talk about all of them. There are several programs, but this is one of the program where Government of India launched back in 2019, National Clean Air Program. It's a program of Ministry of Environment, Forest and Climate Change, and they aimed mainly reducing ambient particulate matter pollution in 131 non-attainment cities across 24 states by about 40% by 2026 related to 2017 levels. And you can see that Maharashtra has almost 19 cities which are considered non-attainment. So what is non-attainment? Means the cities which are higher concentration than the ambient air quality standard. Okay, so what I said in the first slide, seeing is believing. So we have wildfires, we have industrial, we have residential, we have construction, agriculture, wind-blown dust, soil waste burning, haze and smog. We have several different sources of air pollution in the atmosphere. So, we should know what we are breathing and to save our lungs. So I see the pictures here, and I don't think this is really best practice, to do the jog or exercise in this kind of condition. So with that, I thank for your kind attention. I'll be happy to take questions if there are any.
Thank you,
Thank
sir.
you so much, sir. So I request all the participants, if they have any question, they can please ask. Thank you, sir, for such an enlightening and very informative session.
Thank you. I hope I have not taken more time than I was supposed to.
Yeah, no, sir, you are in time. So
No,
participants are requested.
Vinish sir, you can ask question. I have enabled your mic.
Thank you. Thank you. Good evening. Good evening, sir.
Good evening.
So your presentation was very nice, highly informative, and well organized. Thank you for
Thank
the
you.
presentation. And my question is, sir, when you do the air quality modeling, are you an expert in air quality modeling?
I have not done actually. I'm not really modeler. But yeah, you can go ahead with your question. I'll see if I can answer.
So, which kind of modeling approach is needed in air quality modeling? Is it in just like the problems we are doing in CFD, computational fluid dynamics, the same thing can be in air quality modeling also?
I mean, I have not done air quality modeling as I said, but I know colleagues who has been doing modeling. But what I know, the difficulties of doing precise air quality modeling is the data.
Yeah, exactly.
That we probably don't have from everywhere. As I showed the second last slide, air pollution is not an only urban problem. It's also suburban or rural problem. But if you see most of the measurements are done in, let's say, Delhi, Mumbai, Hyderabad, Pune, the urban centers. What about the rural regions? There are several models, ECAM or WRF-CAM, colleagues have been using for even forecasting air quality, or even forecasting fog. Actually, in Institute of Tropical Meteorology, Dr. Gude and group, they have developed model to forecast fog, and they are actually able to do it with a good skill. I must say that, because they have been doing this fog experiment in Delhi at several different places for, I think, the last 4, 5, 6 years, I think. Yeah.
Yep. Exactly, sir. So the data availability is a major hindrance to this air quality
Yeah,
modeling.
of course, because model is I mean, of course, I don't hate modelers. I love modelers, and
Yes.
modelers and the observation people work in synergy. But in model is something that if you input garbage, you will get the garbage.
Yes.
Because it has all the different processes, but what we need to understand, which process to include in the model, right? As I
Okay.
was talking about the secondary aerosol formation, so
Yeah.
we need to know what are the different species that goes into secondary aerosol formation. Then it will be very easy to model, to develop a model for particular those species or their chemistry, to be able to forecast or predict air quality.
That's true. That's true, sir. And most of the state pollution control board has data about criteria pollutants. So when it comes to
Yes.
aerosol, which data is you're using? Is it the data corresponding to the PM 2.5 or something else specifically for aerosols?
I have been using several different data sets. So PM 2.5 or PM10, these are the aerosol mass concentration, which doesn't tell you it just gives the total mass of aerosol, doesn't tell you the size. I mean, like it does tell the size, but it says like all the particle is then 2.5 or 10 micrometer. But the data that I use mostly is aerosol size distribution, where I know the number concentration of a particular size. So
Yes.
that's I think that's probably the most important data, because as I said, aerosols evolve in the atmosphere. Like once they emitted, like the particles that come out of vehicle exhaust, if you measure at the exhaust, it is 10 nanometer or 30 nanometer. But if you track that particular particle, over certain distance, let's say 1 kilometer, that particle will reach up to even 100 nanometer within that 1 kilometer, depend upon, of course, other conditions.
Yeah.
So
Exactly.
in order to understand this, you need a aerosol size distribution.
Yes. Yes.
But
So
it's easy to measure PM 2.5 or 10, right? So of course we should do those measurements, and it's very expensive to measure the aerosol size distribution. That's the
that's it.
problem.
So is there any government agency who's supposed to have this aerosol data?
We have Central Pollution Control Board or State Pollution Control Boards. The data is online, I think, now, since 2017, if I'm not mistaken. Earlier it was not. But I think all the data are now online, especially this PM1, sorry, PM 2.5, PM10,
Yeah.
and other
Is there, sir?
pollutants.
But yeah, what about specific aerosols?
Yeah, it is
PM?
available. PM 2.5 and PM10. These two data sets are available.
Okay. Okay.
Yeah.
And in one of your study, you mentioned that this aerosol concentration is more in central India compared
Mm-hmm.
to Atlantic plain. So what
Mm-hmm.
may be the possible reason you believe?
No, I did not say that. I said that aerosol concentration is higher over Indo-Gangetic Plain than Central India. But what
Yeah.
I said was aerosol loading is increasing much faster over Central India than
Yeah.
the Indo-Gangetic Plain.
Yes. Yes. Yes.
So the main reasons we have not really looked at, but it seems to be biomass burning is one of the cause. Could be construction, or road dust. Could be. I mean, there's definitely not one factor. It's a multitude of factors
Oh,
for that effect.
okay. Okay. Thank you, sir. Thank you. Thank you.
Yeah, thank you.
Sangram sir, you can ask question.
Sir, I'm
Hi.
asking the question related to the suppose satellite image taking at the period of harvesting. आणि that time paralysis means haze created in environment. What effect on the quality of raw data and what effect on the analysis as air pollution occurs in the environment that time?
Okay, in order to do that, first you need geostationary satellite. Because all the satellite data that gives us aerosol data over India, note that these are mostly polar orbiting satellite. So you have measurement at one particular time of the day. And whether you have burning at that time or not, we don't know. Mostly people burn during night, correct? Or evening or early morning. And the satellite I was talking about, MODIS, for example, MODIS is an instrument. There are two satellites, Terra and Aqua. They pass over India at around between 11 and 2, let's say. So it's difficult, okay, with the satellite, unless you have a geostationary satellite. But there are issues with the geostationary satellite because they are at 36,000 kilometer higher up in the space. The quality of that, whether they will be able to detect emission of a small scale emission, I don't know. It's very difficult. They might detect, but of course it will be qualitative. The best is a ground truth. Going in the field or probably the measuring the amount of aerosol that emitted from that particular region, and then of course use models to understand their dynamics, how they transport or how they evolve in the atmosphere. So that would be probably the best approach to what you are asking.
Okay, sir.
Thank you, sir. Is there any question from the participants? Suvarna Chorge, ma'am, you can ask a question.
Good evening, sir.
Good evening.
Yeah, I would like to ask you one question. First of all, I would like to thank you for the presentation you have given. You have been in the time frame and very well presented, and the data what you have given is very nice way. Thank you for that.
Thank you.
I have one question like microwave radiations. Are they a part of air pollutant? Or is there any study?
Are you talking about microplastics, right?
No, microwave radiations.
Microwave radiation.
Yes.
What is it about?
Like we are using all mobiles and all the signal frequencies of higher values. So they are also producing some kind of radiations. These are also harmful for the body and the environment. So are they being considered in the studies which are going on for these aerosols?
No, of course, I am not doing that. But when we talk about pollution, there were several different types of pollution: air, water, noise, and then something else as well. Of course, there are studies which basically talks about the that signal generated by receiving a phone call and so on.
Yes. Yes, that is
But
correct.
I have not really gone to the literature to what extent it impacts human brain or your health or heart. I don't know, honestly.
So, but this is not in the study what you have presented right now.
No,
That is why I thought of
definitely not.
like whether there is a scope of this particular area for research in this.
There is a scope. I think there is a scope because that's what research means, right? Research.
Yeah,
So
that's
there is definitely
yeah.
scope, but we just need to have that state of art technology to do these kind of areas. I seriously haven't thought about it. Yeah.
Okay, no problem, sir. Thank
Thank
you.
you.
But
Thank
I
you.
have one more question. Like you said, there are approaches to go for this analysis of aerosols. So you said one of the method is satellite images also. So how do you compare satellite images method and the one which you said as going on to the fields and doing everything, the analysis. So how do you compare the accuracy of these two methods?
It can be done as long as you are qualitatively looking much larger area. But if you, let's say, want to study air pollution that is coming out from a particular chimney, industrial chimney, that can be also done from satellite. But let's say from residential cooking, in house, how much is aerosol pollution coming out from that? That cannot be done from satellite, right? So for that, of course, you need to go into the field, you need to go to the rural region, go to the house and see how much is coming out of, from residential cooking, for example, there, from the gas stoves and stuff like that. So if you're looking, or a broader region and qualitatively, then you can compare very well. It's a satellite and the ground-based measurements, both. They compare very well in a way. Yeah.
Yeah. So for the large area, you can say satellite images and all, they will help us. Satellite analysis.
Yeah, of course,
will help
course.
us. Okay.
Yes.
Okay. Thank you, sir. Thank you very much for your
Thank you.
information.
Thank you, sir. Any other question? Jyoti ma'am. Jyoti ma'am has raised her hand. You can ask the question. Jyoti ma'am, unmute yourself.
Hello. Good evening, sir.
Good evening.
I just quickly want to ask a question. If we want to do a small study like for a year, and if I choose 3 months, summer, winter, and monsoon, and out of that, if I pick 1 month from each, so will that be effective study? And apart from using the field data, can we use any satellite data for that?
It depends. I mean, you could always do that, but depends upon what you're looking for. If you want to, I mean, you must be having some reason why you are doing this way, right? But this is definitely not the best way. But let's say we don't have that, resources to do the measurements full year. And we could go to the field only for 3 months, then of course I would do what you just said, 1 month from each season, and try to see if there is a seasonality in the aerosol concentration or whatever the parameter you're looking at. It can be done, but you should have proper justification why you did that, then it can be done.
Okay, thank you, sir.
Okay, thank you, sir, for answering so many questions faithfully. So with this I conclude this session. So on behalf of Bharati Vidyapith's College of Engineering for Women, Pune, I express my sincere gratitude to our esteemed speaker, Dr. Vijay Kanavde sir, for delivering such a thought-provoking and enriching session. Sir, your expertise and insights have been truly valuable to all of us. I also thank all the participants for their active engagement and enthusiasm throughout the session. I request all the participants kindly fill the feedback form. The feedback link has been posted in the chat box. Thank you.
Thank you so much for having me. Yeah, thank you everyone. Thank you.
Thank you, sir.
Thank you. Bye-bye. Thank you. Bye.
Ma'am, I'm unable to open the chat box. Can you share the link in the WhatsApp group?
Yes, sure, ma'am. We'll share shortly.
Thank you.